Hello, good morning, everyone. Welcome to the Library Technology Conclave 2021 events. As some of you probably might have participated earlier, I just briefly mentioned that this is our first pre-conclave workshop. We have already had 3 lectures before, and then we are having another workshop tomorrow. So these are the 5 events that we had planned before the actual conclave that will begin on the 27th of January. So welcome to LTC 2021 events and specifically to LTC 2021 pre-conclave workshop on artificial intelligence and eScience. As all of you probably know, Library Technology Conclave is the fifth in the series. The LTC 2021 is the fifth in the series. The LTC Conclave was conceived by Informatics India 5-6 years back, and then they have partnered with different organizations over the last 4 or 5 years to conduct different LTC 2018, 2019, 2021 is now being conducted in partnership with 3 other organizations, the NIAS, that is National Institute of Advanced Studies in Bangalore, and then Rajiv Gandhi University of Health Sciences in Bangalore, and also the CSIR Fourth Paradigm Institute. These are the 3 partners along with Informatics India who are organizing this conference. I am Shalini Aras, I am the program chair and I am your host for today's workshop. So once again, I welcome you all to this pre-conclave workshop. Before I introduce our resource person today, Dr. Mandar Mutalikdesai, I would like to welcome him first, and then a hearty welcome to Dr. Mandar Mutalikdesai. Mandar Mutalikdesai, I guess all of you have read about his brief bio that we have shared before. He is an artificial intelligence practice leader at IBM, and he has done his PhD in cognitive computing as applied to text mining. So this gives you an idea of his depth of experience and knowledge in the areas of large data based computing as well as text mining, which leads to artificial intelligence. And now he's currently, I would call it as a specialist in data sciences and artificial intelligence, particularly the practice solutions. He has got experience offering solutions to his clients in diverse areas, including retail, pharmaceuticals, and various other sectors in the business. So with this brief introduction, I would like to welcome Dr. Mandar Mutalikdesai. And before that, I would like to say he's a dear friend of mine also. We have worked together in different, in different endeavors, let me put it that way. And he has always been, he is a great teacher and a great speaker. So welcome to you, Mandar. Before I hand over the platform to you, see, I just want to talk about since it is about library technology conclave, that alliance between libraries and technologies is a very natural one and it's an age-old one. Since we have artificial intelligence, particularly let us say computing, and then the IBM, because Mandar is representing IBM, let me just narrate a incident or a part of the historical incident about IBM libraries and then the computing in general. See, it was the period of Great Depression, that is the late 1930s and the early 40s during the war, wherein IBM had produced their first 6 big computers. And because of depression, business was down, economy was down. So they could not sell many of their 6 computers. So Watson, who was heading the IBM at that time, well, he was actually depressed because he could not sell and he was trying to expand and all that. And that one evening, his wife invites him for a dinner party. And then reluctantly he agrees to go because he was not in a mood. And in that party, he was seated next to not even a young, smart lady, but an old lady like myself. And then he is further depressed because he's seated next to an old lady and they get talking. And then the old lady asks Watson, what do you do? So he says, I have manufactured this 6 big machines and we have no buyers. So what does it do? He talks about how it can process data, blah, blah, transactions, blah, blah, blah. Then she said, oh, I need them. I'll buy 3 of them. You know, who was that lady? She was the librarian of New York Public Libraries. That is the connection between technology, libraries, and then IBM, because libraries have been one of the early adapters of different technologies, but particularly computers and computing technology. And that's because, and we are one of the, I mean, government agencies and libraries together, I would put it as biggest consumers of IBM machines as well. So with this anecdote, which highlights the connection between computing, libraries, and then the IBM, I'll hand over the platform to Dr. Mandar Mutalikdesai. Welcome, and over to you, Mandar.
Thank you, Professor Shalini. It's a privilege and an honor to talk to this audience today. And it's especially a privilege when you get introduced in an international conclave by one of your mentors. So I will treasure this honor. Thank you so much. And scholarship is something that you find in people quite often, but it's very rare that scholarship and grace come together within one person. And I think Shalini is the perfect embodiment of that. And that's what I have learned from her, that it's important to have grace along with scholarship, right? So it's not enough to just have either one of them. And that's been one of her greatest teachings to me. Thank you so much, and thank you to all the organizers for doing this. I remember that LTC was planned for the previous year, but then a lot of things went south. But I've been following the events, the pre-conclave events so far, and all of them have gone wonderfully well. So I hope that this session will also go well, and I hope that I'm able to add some value to our participants. So can I get started, Professor Shalini?
Yes, please go ahead, Mandar. Just one point. Hello, participants. If you have any questions, please raise your hand towards the end at 11 when the first session concludes. Go ahead, Amanda.
Yeah. Right. Okay. So can everybody see my screen here?
Yes, we can see that. Thank you.
Okay. All right. So as you know, this is supposed to be a tutorial on artificial intelligence, right? So let me tell you a little bit about how this whole idea came about. Professor Shalini contacted me a few weeks ago and said, a few months ago, actually, we've been planning this. And she said, okay, let's talk about AI in the context of eScience, in the context of digital libraries, right? And then I said, okay, now library sciences, digital libraries have been one of the foremost consumers of AI applications. A lot of AI applications have emerged from there when you think about functions like search and semantic search. And I believe Dr. Baeza is going to talk about that in the afternoon today. That's one session definitely not to miss. So a lot of these applications, a lot of these problems came about in the context of digital libraries. So I figured what we would do is we'd talk about artificial intelligence, right? Look at some of its applications, specifically look at what are the different application areas of artificial intelligence, because it's a very broad-based umbrella, and maybe zero in on one of the application areas. And I'm thinking we could go into natural language processing, although there's no reason why you shouldn't be looking at computer vision or speech processing or edge computing or any of the other application areas of artificial intelligence. But for the purposes of today's talk, we will focus on natural language processing as an application area of AI, and we'll look at some techniques of AI that can be applied in the context of a running example. I have a use case, a running example that kind of takes you through various stages of designing an AI solution. So I hope I hope that makes sense to everybody. And like Professor said earlier, if anybody has any questions in roughly about an hour from now, we'll definitely take those questions and discuss. So let's start with the basic question. What is artificial intelligence? And I want to begin by saying there is no one right answer to this, obviously, because the field itself is evolving so rapidly. Our understanding of the field is evolving so rapidly. I think it would be foolhardy to kind of try and tie it down with a single definition, right? Now, if you look at the gentleman there in the picture, uh, this that's Alan Turing for those who do not know, and that's the contraption next to him. That's the Turing machine. Well, visual rendering of the Turing machine, an artist's impression of the Turing machine, right? So I think it's undeniable that the notion of computing that we have today, the notion of the algorithm that we have today, we owe it to Alan Turing, right? Now, the moment you are able to start computing, the moment you are able to bring in efficiency and insight into your day-to-day life, into your applications, using computing, I think you've already achieved artificial intelligence, right? And once you have the notion of computers, and you can then start looking at them as bots, as intelligent agents, which is how a lot of computing works today. You have a multi-agent system of autonomous agents, each capable of making decisions for themselves to maximize their own payoffs, but at the same time working together with other bots and agents in order to achieve a global objective, right? So from the notion of computers, it becomes possible for us to achieve a notion of intelligent agents and them working together, collaborating with one another. Of course, that leads to problems like them also trying to compete with one another sometimes. Sometimes they go rogue and so on and so forth. But that's a separate area of study by itself. So we won't go there for now. So uh, and then you incorporate learning among these agents. You give them the ability to reason. You figure out how to make them reason, what kind of algorithms would look at data and help reason that data. You help your computers or your algorithms develop an understanding of the world around it, right? And to add to this, if you can also put in explainability, right, I think that the sum total is what is known as artificial intelligence. But like I said, there is no one definition of AI. I'm very sure that pretty much any person that you talk to who has worked in this field will have a different interpretation of what AI is, and that's just the way it is. So, like I was saying, the earliest applications of AI in terms of search, semantic search, and cognitive models, natural language processing, they have actually taken root in the context of digital libraries, right? In fact, a lot of projects that were funded by government institutions like DARPA were in the context of library technologies and digital libraries, right? So let's quickly trace a history of AI in general, right? So on my screen, you see a timeline of up to roughly about 2000. This is not entirely accurate, down to the year, but it's a good representation of the sequence of events, at least the main ones that led to the evolution of AI the way we know it today, and of course it will continue to evolve. So before say around 1950 or the late 40s, artificial intelligence was entirely in the realm of fiction. It's not like people did not, it's not like it was inconceivable. There was artificial intelligence, but you read about it in novels, right? You read about it in the novels of Jules Verne and Arthur C. Clarke, and so on and so forth. But around 1949 is when the first stored program computer was invented called the Manchester Mark I, which eventually became one of the computers that IBM co-developed. And in around the same time, Alan Turing wrote his seminal paper, "Can Machines Think?" And from there on, about 5 years later, a very interesting program known as logic theorists was developed. Now, whenever in the history of mankind, whenever there has been an effort to develop AI, to achieve AI, right, it has been done with several different objectives in mind, right? In 1955, logic theorists had the objective that it wanted to prove theorems, right? And specifically, the theorems that they wanted to prove were the ones from Principia Mathematica. You may have heard about Principia Mathematica, Alfred North Whitehead, and Bertrand Russell's famous tomb. So eventually, logic theorists was able to prove, I think, a large chunk of the theorems, about 38 out of the 50 theorems in logic theorists. In Principia Mathematica. So that was one of the first big steps, that led us to believe that it is possible to achieve artificial intelligence for various objectives. Right. Let me pause there for a moment, and let's just focus on that notion that artificial intelligence is an objective, right? Many times when we talk about AI, we tend to talk about it as if it's a technology or a suite of technologies, right? It isn't. Artificial intelligence is an objective. It is something you want to achieve. And there's a host of technologies, there's a host of computing paradigms, learning paradigms, reasoning paradigms that help you achieve that artificial intelligence, right? At the very basic level, that artificial intelligence could be achieved with, say, developing a very basic expert system with simple if-else statements, and that's still artificial intelligence. You could develop artificial intelligence with machine learning the way we know it today. You could do unsupervised machine learning. You could do some clustering of your data, and that's artificial intelligence. You could build a classifier. You could have a neural network do a task for you. All of these techniques eventually lead to the same goal, the achieving of artificial intelligence. Similarly, there are other ways you could achieve artificial intelligence. Machine learning is just one of them. Cognitive computing. At IIIT Bangalore, my former thesis supervisor, Professor Srinath Srinivasa, and a couple of others in his lab, we started working on some non-machine learning based paradigms for achieving artificial intelligence, which eventually which we called cognitive computing. That kind of became a part of that body of research. So anyway, continuing with the timeline here, there were several. DARPA actually ended up funding several initiatives at Dartmouth, at MIT, and eventually Moore's law came along because the development of hardware to support these mathematical notions of computing was becoming more and more mature. So we're all familiar with Moore's law. That was around 1965. And around 1968, basically the late 60s and the early 70s, is when there was a lot of speculation about how AI would grow and how quickly it would grow. In 1968, for example, Arthur Clarke and Stanley Kubrick. And it's interesting that they should come from two people in the realm of creative arts, Arthur Clarke being a writer, and Stanley Kubrick, also known as Steve Kubrick, was a filmmaker, made some phenomenal films, right? So these people said that by the year 2001, we will have machines with intelligence that matched or exceeded humans, right? And for them to make that prediction over 30 years ago, 30 years before this time, with a 30-year timeline in mind, was something, right? And sure, I don't think we still have achieved that kind of artificial intelligence that matches or exceeds humans. I believe we're still far away from that kind of general intelligence, but we have started making strides, right? So if you've taken a look at the recent developments with GPT-3 or with DALI. DALI was just I learned of it just about a couple of days ago. uh, we now have AI that can perform tasks with declarative input. So you could ask GPT-3 to build you an HTML page with a blue button in the middle of the page, and it will actually generate code for you, right? And DALI can generate an image based on the textual description that you give, right? So we have we have started achieving the kind of artificial intelligence that Clark and Kubrick talked about. But yes, what Minsky said in 1970 was that from 3 to 8 years, we will have in 3 to 8 years we will have a machine with the general intelligence of a human being, and he said that in 1970. So forget the 1980s. Even today, we do not have machines with that kind of general intelligence. So not all predictions have been on the money, but I think it is great that there was that kind of a movement in the computing world that enabled people, that made people feel like they could actually go ahead and make those predictions. I think that is it's encouraging that they felt encouraged to make those predictions. Then expert systems, uh, uh, made an entry in 1980 by Edward Feigenbaum. uh, NavLab developed the first autonomous car. CMU built this. Carnegie Mellon built this. That was 1986, long before either Google or Tesla had started working on this problem, right? So we have been making consistent breakthroughs in the field of AI, uh, and over decades after the breakthrough, we are actually even seeing industrial application, large scale application of those breakthrough. Late 90s, Deep Blue by IBM beat Gary Kasparov in chess. Then Dragon Systems made the first made public their first speech recognition system, and so on and so forth. Early 2000s was the time when deep learning started, peaking. Deep learning as we know it, although I feel like it's largely old wine and new bottle. I know I'm being a tad unfair when I say that. Neural networks have been around for a long time, but what happened in 2006 is there were a lot of advances made in the field of neural networks itself, right? In terms of developing convolutions, the notion of convolutions, for example, the way we know it today, in order to understand image kernels. I think those developments built on the platform of neural networks is what made deep learning, uh, you know, what it is today, right? So 2011, IBM Watson won Jeopardy. I think that kind of opened the doors for companies like IBM to commercialize AI and start building solutions for the various verticals of business. In 2016, AlphaGo beat world champions in that game of Go. And just like I mentioned a little while ago, GPT-3 and DALI are the latest and the greatest. So do take a look. Some really fascinating technologies, both of those. OpenAI is the organization that's been developing them. So like I was saying, there are several application areas of artificial intelligence, right? So there is natural language, where it could be applied in terms of processing natural language, understanding natural language, generating natural language, and the same with synthesizing speech, understanding speech. And when I say natural language, I'm just talking about text, right? So when you bring in speech, that brings in additional complexity of understanding what's being uttered as well, right? And then you have computer vision, which is largely problems like being able to do visual recognition, recognize specific objects within images, being able to tell what's happening within an image. And once you do that, it opens up a whole array of possibilities for you, including say monitoring and surveillance. And if you have a stack of coins and you take a picture of it, maybe you don't have to sit and count the coins yourself. Your algorithm will now count the coins for you, recognize this object as a stack of coins, and then segment them into individual coins and tell you how many coins there are, right? So there's several applications like this. There's ontological reasoning, which is again definitely an application area of artificial intelligence. There's cognitive reasoning, and so on and so forth. But for the purpose of today's talk, we will take natural language as kind of an a running example of one AI area, right? And then look at some techniques, which we will apply in the context of natural language. But whatever techniques we talk about today, what I want you to take with you is that first, whatever algorithms, whatever techniques we talk about, by no means is it going to be exhaustive. It's just one small, very small effort being made to kind of introduce this topic of AI. This is an introductory talk. I'm sure you all understand that. What I want you to take with you is that is just the idea that given one area of AI, how do I go about solving a problem? How do I go about building a solution? Right. That's the focus of this talk. And then feel free to go ahead and start thinking about building a solution in any of these other areas that you see on your screen right now. Right. So natural language, as we all know, is kind of the final frontier. Yeah, and when I say natural language, just understanding text is difficult enough. And when you add speech into it, that modality just makes it even harder, right? There is natural language processing, there is understanding, there's natural language generation, right? So those are the three things that you have to address when you talk about natural language. But let's focus on just natural language processing. So I'm just trying to kind of, refine the topic, right, for today from a very broad and generic notion of AI to natural language down to natural language processing. And now I'm going to introduce one example, one problem, and we'll walk through that problem, the various stages of the solution to that problem, to understand what AI techniques can we use in order to solve those problems, right? So when it comes to natural language processing, you have various, various standard problems, right? Such as recognizing parts of speech, parsing a sentence, generating parse trees, recognizing named entities, information retrieval, and Ricardo will talk about it in the afternoon. The organization of that information in terms of creating meaningful clusters, meaningful classes or categories. So these are just some of the problems that are in the realm of natural language processing. Now, natural language processing was that it was about how do we generate, how do we come up with algorithms that can do all those tasks, parts of speech, identifying named entities, classification, clustering, and so on and so forth, right? Now, natural language understanding, on the other hand, right, is a trickier problem. While natural language processing it can be based firmly in computing, right? Natural language understanding is not just an out and out computing problem, right? Because when you talk about natural language understanding, right, there's one main thing that we need to keep in mind, which is that natural language is something that helps people preserve their most natural mode of communication. That's just their most natural mode of expression, right? Which means that when they express something in whatever language, they incorporate language They incorporate idioms that are contextualized to their culture, to their geography. Maybe economic factors play a role there. There are accents involved, there are dialects involved, there are belief systems involved, right? Whatever people speak reflects a lot of their belief system. They state that idiom as if it's a given, right? Because it's highly contextualized. Now, if you're going to address the problem of natural language understanding, alongside being able to do some of these standard tasks like recognizing parts of speech, etc., you would have to understand the context, the semantics of the language itself, right? What's the culture in which it is being spoken about? How does the geography influence that idiom? What kind of belief systems are influencing that idiom? uh, and accent and dialect, of course, is a given, right? And then over and above that, there are the social and temporal norms as well, right? For example, I think it was about 6 months ago that I got a text from I help run a community of book readers here. There's a book club that I help run in Bangalore, along with a few others. And one of the organizing members of that group, a very young person, she texted me and said, "Hey yo." And I did not know what that meant because for me, I'd never heard that word before. So I had to look it up. And "hey yo" is, so it seems to be some sort of a combination of hey and yo. And yo itself, I don't know what, I still don't understand what it means entirely, but net, hey yo is a greeting, right? And I'm pretty sure that that's not a word that has existed in the English vocabulary since forever, right? It's language evolves. That's the point. Language evolves. Social and temporal norms cause the evolution of that language. As a culture evolves, the language will evolve, and you will need to address all of that. So whatever AI we talk about in terms of natural language processing, natural language understanding, that AI has to evolve if it is to assist us with developing applications in natural language to keep up with the evolution of the natural language itself. And natural language generation, of course, is the holy grail, and we're going to stay away from it for the purposes of this talk. In fact, whatever I've spoken about so far is just for me to lay that groundwork and come to this particular case in point, this particular application, a problem. Okay, and this is what we're going to use as a running example, and we'll break this problem down and take each part of the problem and solve it with one particular technique in AI slash NLP, natural language processing, right? So here's the problem. Assume that there's a bank. Okay, so there's a large bank which specializes in onboarding high net worth individuals, right? There are several banks in the world that do that. So when a high net worth individual approaches a bank, the bank now has to decide, do I onboard this customer? Which means, do I open an account for them in my bank? Do I give them a vault in my bank? Do I give them a locker? Do I let them invest in my schemes, and so on and so forth, right? But before they onboard a customer, now even in regular banks, right? Um, when we go and say, hey, I want to open an account in your bank, they tell us, okay, give us your PAN card, give us your address proof. So there is KYC that happens, right? But the KYC that's done for regular banks is kind of, the scale is very different. I'm talking about these banks for high net worth individuals because it presents a very different set of challenges, right? Knowing a customer, the KYC, know your customer for a high net worth individual is not just about getting details of their PAN card or their Aadhaar card or their address proof, right? It's about understanding what has been the track record of this customer. Will this customer bring value to the bank? Will they cause problems to the bank? For example, what do the newspapers say about this person, right? Do we see that this person is involved in a lot of controversy? Do we see that this person has been inciting hatred and violence, or do we see that there is litigation against this person? Do we see that this person has been involved with narcotics? Is there political exposure? Is there a politician just 1 degree separated from this person? In which case, the bank might think twice because they don't want politics to get, get kind of mixed up with their business. So these are the kind of questions that the larger banks for high net worth individuals will want to ask, right? Which is very different from the KYC that we generally hear about. So I want to focus on that problem. I understand it's a bit elitistic, that entire notion itself, but that's a separate problem to solve. But the reason I want to focus on that problem is because it presents very unique challenges. So what would the solution look like? Now you have to develop a solution. Let's say you are the solution architect, and you have to develop a solution that helps you develop a KYC system for this bank, right? You have to basically automate this. Like we said, we are going to look at information that's present in newspapers and on websites and on blogs about this person, which means that you cannot possibly sit and manually scour through all this information on the web and come to a conclusion. That's going to take several weeks, maybe even months, right? The question is, can you now boil this down to a matter of a few hours or maybe just a few days, right? In the worst case. So which means that you're talking about uh, being able to represent millions of pages, web pages, and to a computer, which means you have to be able to crawl those pages, extract information from those pages, and then do meaningful computations on that data in order to get some insights about this customer, right? And we're talking the scale of millions. Then once you look at an article, once you have a specific article, you want to understand what is the topic of this article, right? Which means that you want to say, okay, is this article talking about a betting scandal? Is it talking about something else? What exactly is the main topic of this article? And then there is an issue about how do you now store this information. So once you've understood that you have, once you understood that this article is about narcotics, then how do I go ahead and organize this information, right? How do I separate information from noise? Because this is the web and it's free for all. So there's hardly going to be a case where you are able to crawl just a few pages that cogently give you the information that you need, right? So your information is like finding a needle in a haystack. How do I separate my information from all that noise? How do I correlate information, right? And there's several other challenges like this. So you need to solve this sequence of problems in order to build a solution. Now, let's start with the first one. Let's start with building this KYC solution. Now, let's start talking about how do we deal with this problem of representing millions of pages on the web, right? Now, here is you have text, right? You have text written on these web pages. Now, this text is written in terms of, it's a document and it's written in terms of sentences, which is again boiled down to the level of words. Now, this might be a bit basic for some of you, but I think just as well, I'm not sure if everybody here in this audience is familiar with document representation. So I'm going to talk about a very, very basic technique to do that. So there are various ways in which you could take a document and represent it mathematically. When we talk about representing millions of pages or even just one web page or any document, it's about representing it in a way that a computer can understand it, which is to say that I need to find a mathematical way of representing a document. So what is a mathematical equivalent of a text document? There are several ways that could be done. One is that you simply look at the document as a bag of words, which means that you take this document and you say every word here, right, is just a member of a set. The document itself is a set or a multi-set. So the set has a constraint that every element has to be unique. If you relax that assumption and say that a set can have repeating elements, then it becomes a multi-set or a bag. And you just treat this document now as a bag. So now your document is a set or a multi-set. So that's one way of representing a document mathematically. Another way of representing a document mathematically is to represent it as a graph. You could say, okay, I'm going to look at all these words and map their co-occurrences, right? So what is that? The quick brown fox jumped over the fence, blah, blah, whatever is the sentence, right? So quick, brown, fox, fence, all of these have co-occurred within the same sentence. So you could now make them as nodes and put an edge between every pair of nodes and say, okay, this click represents one co-occurrence within one sentence, right? So it's just one way of representing a document as a graph. So if you represent an entire corpus, you will have a large graph with several small clicks embedded uh, inside that graph. So that's another way. The third could be to represent documents as vectors. Now, what does that mean? We'll actually look at vectors in a little bit more detail, but at a very high level, what we are talking about here is to take a document and represent it as a point in space, in a multidimensional space, right? So for the purposes of our talk, I'm going to assume a three-dimensional space and help you visualize how a document can become a point in that three-dimensional space. So you can just imagine the document becoming a point in the room that you're sitting in. And from that follows other forms like shingles or engrams, which is to say, you will not look at individual terms, individual words, but you will look at a window of terms at a time, right? For example, if you say, I will look at 2 grams, it means you will generate a window of size 2, and you'll look at 2 words at a time that occur consecutively. So as you move this window, what are the 2 words that appear to you within that window? So that's how you will start looking at a document. And then again, you will either represent it as a bag or as a graph or as a vector, right? And then you have higher dimensional representations and word embeddings such as word2vec, glove, doc2vec, and so many other innovations in that area these days. I'd encourage all of you to go and take a look. Several of them are usable as Python libraries without much effort. So go ahead and play around with it a bit. I don't think we will have time to go into word and document embeddings in this talk, but I just wanted to introduce that notion to you. Right, so let me just see how we are doing on time. Okay, I think in about 15 minutes, we'll kind of open this floor up for questions, and that's session 1, right? Okay, so a vector space of documents, right? So when I said earlier that representing a document as a vector means that you would represent each document as a point in space, right? Now, in order to do that, you would have to imagine that the dimensions of the space are the terms, are the words, right? And once you look at, so just look at the room that you're sitting in, pick one of the corners and call that the origin. And from there, you will see there are 3 dimensions that are emerging, right? Now, if you assign one word for each of those dimensions, right? Quick, brown, fox, let's say those are the 3 words. Now, if there is a document that has quick occurring twice, brown occurring once, and fox occurring 5 times, then 2, 1, 5 is the document representing that, is the point representing that document, right? Because the x-axis was quick, and that occurred twice in this document. Brown occurred once, that was y-axis, and the z-axis is fox, which occurred 5 times, right? So 2, 1, 5 is the point that represents this particular document, right? And vectors are essentially that. So we here, especially in schools that I went to, every time we talked about a vector, they said, what's a vector? A vector is something with magnitude and a direction. And it really didn't mean much at that point, but it helps to visualize that a vector is essentially a point in a metric space, and When you talk about magnitude, you could think about it as its distance from the origin, the distance of that point from the origin. And when you talk about direction, it's essentially the angles that it is making with each of the dimensions. So, right. So here's another example, right? So now the names that you see on this slide, they're actually names of students of Professor Shalini and I from several years ago. So I'm very grateful to them because even today I use their names as, I guess I made this slide for their class for the very first time and just liked it. So I retained it. So document 1 is Gagan and Sunil are friends. So are Sunil and Rashmi. That's document 1, right? 2 sentences. Document 2 is Soumya and Rashmi are friends, right? So when you put both the documents together, let's say the corpus is just these 2 documents, and when you look at the entire corpus now, you have 5 unique terms. Let's remove all the stop words such as and are, etc. Gagan, Sunil, Soumya, Rashmi, friends. These are the 5 terms. So we now have a 5-dimensional space in which we can represent D1 and D2, right, as vectors. So just go back to the quick brown fox example, and that should help you kind of visualize how this vector is going to get constructed. Right. So in the first one, what was the first sentence again? The first document, it was Gagan and Sunil are friends. So are Sunil and Rashmi. So Gagan occurred once, Sunil has occurred twice. All right. Okay. So let's see here now. So Gagan occurred once, Sunil twice. Soumya did not occur at all because that term occurs only in the second document, not in the first document. Rashmi once and friends once, right? Now, if that's the order in which you're going to represent your dimensions, Gagan, Sunil, Soumya, Rashmi, friends, then D1 is 1, 2, 0, 1, 1. And similarly, D2 would become 0, 0, 1, 1, 1, right? Now, this is probably one of the most fundamental ways of representing a document. It's a very basic way of representing a document using just the term frequencies. And in general, when you try to solve problems in natural language processing, it is not enough to just use term frequencies, build vectors like this, and you can't hope to solve a problem very well doing that, but it definitely lays a good foundation for you to start thinking about the problem. Now, from here on, we kind of refine this idea a bit and say that just using the frequencies of terms is not enough because not all terms are equal, right? For example, if you're trying to represent a corpus from ESPN Cricinfo, the word cricket is a non-trivial word in any other context. But in the context of ESPN Cricinfo, you can expect that the word cricket occurs pretty much in every document, right? So if you have the word cricket in ESPN Cricinfo and you have the word, say, the term Mahendra Singh Dhoni, do you think both those terms are equally important? Probably not, because not every document on ESPN Cricinfo will talk about MS Dhoni, but every document will talk about cricket, which means that if you see the word cricket in ESPN Cricinfo, it's not really going to surprise you, right? It doesn't really do much to your information gain. But if you see the term Mahendra Singh Dhoni, you know that there is information gain here because you expect to see something specific about Mahendra Singh Dhoni. So then you start kind of weighing the term frequency down by how commonly it occurs across all the documents in your document space. Right. Now, when we talk about representation, right, we have just now talked about representing documents. But remember, we had started with this lofty ideal of being able to represent language. Now, have we done that? What we have done is we have broken down a document into tokens, into terms, and we have gone ahead and represented it mathematically, either using a bag or a graph or using a vector space, right? But we have ignored linguistic structure. If there was any idiom in that text, we have completely ignored it. We have represented content, we have not represented language yet, right? And I certainly don't mean to claim that we can do that in today's session, or that we can do it effectively at all. I think much of that is still work in progress, but I just wanted to make you aware that while we are talking about representing documents, we're still not talking about representing language itself, right? Language is a far more complex construct. So that leaves us with the question, how do we understand language, right? Now, there are some techniques you can use in order to quote unquote understand language, right? You could do tokenization and break them down into terms, which is what we have done. You could look at, what have been the rules of production, what is the grammar of this sentence, right? And that might give you some insight into the nature of this language, right? How do you decode the sentence, what kind of encoding has been used in it, what are the building blocks, what parts of speech have been used in it, what's the order in which these parts of speech occur, how does it help in building a coherent sentence, how do phrases get constructed here, which might answer the question, how does complexity get infused into the language, how does context get embedded through idiom, right? That so those are the problems that really need to be solved. And I think for the most part we conveniently ignore some of these problems altogether even today, right? Well, I say conveniently, but really the reason is that we are not yet there. I mean, we do not yet have the means to say uh, uh, understand the context of a document. A lot of research has been happening. I know research has been happening at IIIT Bangalore, for instance, and there has been research like GPT-3, which does a great job in terms of understanding idiom complexity and so on, but it's still early days. And the other thing to remember here is that so far we have not talked about languages, we have talked just about documents. That's one thing to remember. The second is that we have talked only about English. We have not talked about any other languages. So English is probably the simplest language to parse. And yet it's not simple enough, of course, but it is still the simplest one to parse, because a lot of work has already gone into it, probably one of the most spoken languages in the world. But what about local languages? What about agglutinative languages, right? Languages such as Indian languages. And I know that a lot of South Indian languages especially are agglutinative, which means that you can fuse words together to form a single notion, a single word again, right? Which you cannot do in English. For example, and it's not just sandhi I'm talking about. So ಮಾಡಲಾಗುತ್ತದೆ, ಮಾಡಲು ಆಗುತ್ತದೆ, ಮಾಡಲಾಗುತ್ತದೆ. So words get fused like this, right? And it's still not a great example for agglutination, but I'd encourage you to look it up. When you look at local languages, when you look at properties like agglutination, parsing becomes a lot more complicated, right? When you see words getting fused to coherently form other words that mean the same thing, that provide a lot more richness to the language, parsing such languages becomes a lot more difficult. And again, in the field of computational linguistics, there has been a lot of work that has gone on in understanding some of these languages. So in the interest of time, I'm going to skip, parse trees and move on to the next part, which is understanding the topic of an article, right? Now, topicality of text can be understood, and I'm not going to spend too much time on this part. You could either syntactically understand topicality in text by identifying nouns and noun phrases, named entities, and so on, or you could follow a semantic approach and say, okay, what are the semantic roles that I can assign to the agents in a sentence. For example, Shalini gave 10 rupees to Mandar. If suppose that's the sentence, right? Then what does semantic role labeling do? It basically assigns the status, the label of giver to Shalini and taker to Mandar, right? So assignment of such semantic roles in a sentence or in a document can help you understand what kind of actions are taking place, what is the context of the document, what kind of topicality exists in it. Or you can look at topic modeling, co-occurrence analysis, word clouds, and so on. Right. So, like I was saying, I just talked about semantic role labeling, so let's not spend too much time on this slide either. But it's about identifying what role each term plays in a sentence, right? And I would encourage you to go and take a look at libraries such as Allen NLP. You can play around with them, fairly easy to import it and use it in your code in Python. And of course, there are techniques like LDA and LSI, which help you, understand topicality in terms of emergent semantics, in terms of topic modeling, and co-occurrence analysis. There's been some excellent work done at IIIT Bangalore at the Web Systems Lab. Please go and take a look at some of the papers that they have been writing. Right. Let me now come to the organizing information part, because that is where we're going to talk about some of the techniques, some of the AI techniques, quote unquote, that help us solve this problem. Right. So organizing text, at a very trivial level, could mean full text indexing and similarity, classifying documents, clustering documents, etc. Right now, for indexing and retrieval, I think there is a talk about it in the afternoon, so let's completely skip that, and that's not the focus of my talk anyway. Now, when it comes to similarity measures, right, I just want to talk about this a little bit. Whether we want to solve the problem of classifying documents or clustering them, or pretty much any problem in natural language processing, the most basic thing that you'll need to do is understand how similar or dissimilar two documents are, right? Now, there are various ways in which you could measure the distance between two documents, or the similarity between two documents, right? Now, let's assume the vector space model itself, right? Like earlier. So imagine your documents to be points in a multidimensional space. Now, you would say that similarity is basically an inverse of the distance between any 2 points. So document D1 and D2, how similar are they? Basically, the inverse of the distance, the spatial distance between them. And that distance you could either measure in terms of an L1 norm, or the Manhattan distance, which is essentially how a taxi driver drives in Manhattan, or as I like to put it, in Jayanagar 4th block, because Jayanagar 4th block is also a grid, like Manhattan. So it's not as the crow flies distance, it's as the taxi driver drives, right? So it's essentially, X plus Y, right? And then you have the as the crow flies distance, which is the Euclidean distance between 2 points, right? And you could generalize this. So L1 norm is the Manhattan distance, or the taxi driver distance. L2 norm is the Euclidean distance, which is the straight line distance. So there is a notion of LP norm. You can generalize it to the LP norm, and just look at the equation that I have there for LP. Now substitute P equals 1, you have the Manhattan distance, right? So x1 minus y1 plus x2 minus y2 plus x3 minus y3, that's exactly what Manhattan distance is. Now put P, make P to be 2, and you get the, it's essentially square root of x1 minus y1 squared plus x2 minus y2 squared, and so on, right? And that is the Euclidean distance. But probably the most effective way of measuring the distance, or the similarity between two documents, is to measure the cosine distance between them, right? Which is to say, what's the angle that is being made by those two vectors. So D1 and D2 are two documents, they're points in space, two vectors. So what is the angle that they make with each other, right? What is the theta between them? and measure the cosine of that angle. Now, this is useful. Suppose you have two documents, D1 and D2, and say D2 is just a scaled version of D1, which means, let's say D1 is Gagan and Sunil are friends, and D2 is Gagan and Sunil are friends occurring 3 or 4 times. Okay. Now, the Euclidean distance between these 2 points is going to be high, but the angular distance between them is 0 because they are along the same straight line from the origin, right? So if you have the issue of documents being scaled versions of one another, then cosine is probably the easiest way to represent distance. Okay, so I'm going to pause here for a bit and see if there are any questions.
Yeah. Hello, good morning, participants. I see some 2 people had raised questions. One, I think, is Saktivel Sami. Could you raise your hand and then ask your question?
There are 4 hands raised, actually 5 hands raised now.
Right. Okay. Allow these 5 people to ask the questions first.
Okay, Mr. Naveen Kumar Nayak.
You can activate the video also there.
Sure. Mr. Naveen, you can unmute.
Mr. Naveen Kumar Nayak, you can unmute and ask your question, please. I think this other person is also now on.
Yeah, Mr.
Whoever is Saktivel Sami.
Yeah, can you hear me?
Yeah, we can hear you.
Yeah,
You
good
can
morning.
share your
Good
video
morning.
also. Yeah, go ahead.
Yeah, my question is that basically I'm working on with various. Hello.
Yeah, go ahead, please.
Go ahead.
So we are working on machine learning and deep learning techniques for weather forecasting and predictions. So do you suggest any other techniques which is being available for AI, something like that? Do you come across any kind of methodology kind of things?
Well, I don't think I have enough information to give you a meaningful suggestion. It's interesting that you're working on weather prediction problems, and you said that you are employing deep learning techniques already, right?
Sorry?
So you said you're using deep learning techniques.
Yeah, machine learning, deep learning, we are using it for weather forecasting kind of things.
Okay.
So do you have any, I mean, any one of your group or somebody else, they are working on this kind of technique like that? I mean, may not be you directly, your friend circle or somebody else, or your colleague, somebody else.
Yeah, I mean, we do work on problems in predictive analytics, and it sounds like that's what you're going for. What I would be interested in is what specific techniques are you currently using? When you say you're using machine learning and deep learning, what are you doing precisely? What kind of neural network architecture do you have? What what accuracy you've been getting? What's your training accuracy? What's your validation accuracy? What's your training loss, validation loss, things like that. So if based on that, maybe I could help you make changes to your architecture. That's possible.
Yeah, fine. If you can share me your email ID, then I can write to you in detail. Then we can take it up later stage.
Sure. So I will ask Devendra to share my email ID with you later.
Yeah, fine.
Sure, it will be done.
Yeah. Thank you. Thanks a lot. Yeah.
Mr. Vivek Kumbar.
Yes.
You can ask, sir. You can ask question.
Sir, I already put my question in the question box. Could you see that?
Okay, I'll read out for you. How can we use artificial intelligence in daily routine works of library? What are the open source software of artificial intelligence for use in libraries? Could you please show the demo?
Yeah, I certainly don't have demos, but I want to ask you a question in turn. So can you mention specific tasks that you'd be interested in? Because
Especially in
we could generally talk about, say, for example, if we assume a digital library, and suppose you are talking about a host of novels, let's say, right? How do we organize these novels by genre, right? Or textbooks, how do we organize these textbooks by subject or by genre, right?
oh,
uh, that is
to
one problem, but do you have something specific in mind?
yeah, according to the classification scheme, we will organize like UDC and DDC. Based on that, we'll organize the collections in the different parts.
Right, so if that's the problem you're looking at, and let's say you are developing a large scale digital library. Let's say you're one of the product managers for Kindle, or for you're managing the library at the University of Mysore or somewhere, and you now want to organize a whole bunch of books by genre, right? For example, you come to a specific set of books which are all novels, right? Now it is easier to organize textbooks and reference books, because more often than not the topic of the book is evident when you look at it, right? It's fairly easy to infer the topic of the book. But with a novel, it's extremely difficult to understand what's the topic. What does the topic mean in the case of a novel? In that case, you could look at developing a classification system. If you have, say, a global list of genres, say about 25, 30 genres or whatever, right? You could now start building a model for determining what genre a particular novel belongs to. So for doing that, you will need to first, I'm assuming that you have digitized versions of these novels and you have been able to extract all that information, and you're able to represent the information in that novel mathematically. Now, once you've done that, uh, you will need to have an initial set of novels that are labeled by hand, to say that, okay, this novel is science fiction, and this novel is literary fiction, and this novel is crime fiction. So if you have enough samples, right, that you can call your training data, right, then you can start building a model. You could look at classification algorithms. You could look at, say, start with the naive bayes. It's a fantastic algorithm, works more often than not, and it doesn't receive its due credit usually. So a naive bayes algorithm will now basically start learning patterns, right, about what makes a crime fiction novel a crime fiction novel, right? So you said that this is a crime fiction novel. It will try to identify what are the inherent properties, what are the inherent probability distributions that exist within it that make it crime fiction. So next time it sees another document with similar properties, it will flag it as probabilistically flag it as being a crime fiction novel, right? So does that help? Does that answer your question?
If I may intervene, Mandar, I think what he's asking is about, see, in the library systems, usually there is a classification system that he mentioned, like DDC or colon or any other system that are in use.
Mhm.
So he wants to know whether he could use AI. I mean, essentially, I think what he means is an automatic classification. But your answer would also mean that. Only thing is, I would say, perhaps, as you say, a training set of samples where they have already predetermined and then, given the class number, etc., to those novels or any books.
Right.
Is that what you had in mind, Mr. Vivek Kumba?
Yes, madam. Also, in reference query, reference service, can you use this artificial intelligence like some AL is providing Ask Librarians the services, some AL other institutions. Similar like that, can you use this artificial intelligence providing robotic technology in terms of reference service also? How we can
As I know, some of the libraries are using this chatbots for answering simple queries. That's one of the things where they have kind of already implemented. like the reference queries, the reference service that you are asking for. Simple questions when they ask the library people, it's answered by these chatbots. That's one example that I know of. Mandar, you could elaborate on that?
Yeah, so like Professor Shalini said, chatbots is one kind of solution that can be deployed in a library setting. So you can now ask questions and get answers. So the questions could be as simple as, where can I find a certain book? Which alley, which shelf do I go to find a certain book? Or it could also be about, can you tell me what is this particular book about, right? So the questions could be of varying ranges of complexity. But I think I'd like to kind of differentiate what is available, right, in order to implement a solution, right? At the very highest level, you have ready-made solutions, right, for library systems, right? Now, I am not personally aware of any ready-made solutions that are built for direct use in libraries, right? So these are offerings. Now below that, you could think about, okay, some assets that already exist. For example, chatbots. They are generic, but they can be used in the context of libraries, right? Whereas the solutions that we talked about earlier, the offerings, they are specifically built for libraries, right? Now I'm not sure of those, but at the next level, things like chatbots, yes, those can be used in the context of libraries. Now you go one level below that, there are programming libraries, and I mean programming packages, right? APIs available, using which you could build your own solution in order to use in your library. Now these APIs, you would still need to write your code, you would still need to develop your solution, but these APIs kind of encapsulate a certain amount of complexity. So it kind of abstracts away a certain amount of complexity from you. For example, I saw a question earlier from somebody here. They were asking, what library can I use for semantic role labeling? There is one library called Allen NLP, right? Now, ALLEN is the name of the library. Now, Allen NLP will allow you to go ahead and simply call the API and do semantic role labeling given a sentence. How the semantic role labeling is done, that's detail that is abstracted away from you, right? So there are libraries like that, right? And one level below that is, it's just pure code. You need to define your own functions. So when you talk about building a solution for a library, right, you have to look at these four different levels of abstraction. Building everything from scratch by yourself, using existing programming packages and libraries in order to make your life easy in building your applications, or using pre-existing solutions and building your solution, building your application, or using something that's ready-made available for you off the shelf as an offering, right? So I think chatbots would fall into the second category, but there is this entire stack for you to look at.
Devendra, who are the others who had raised their hand?
The next is Navin Kumar Nayak.
Naveen Kumar Nayak, okay.
You can unmute yourself, sir. You can put your audio also and video also on, no problem.
Naveen Kumar, unmute and you can switch on the video and ask your question.
Naveen Kumar.
Okay, in the meanwhile, we can ask Anil Gupta to please unmute yourself if you have any question. Mr. Anil Gupta?
There is at least a question in the chat box by Priya R. How do we handle the co-occurrence of words, especially for regional languages? I don't know whether you have unmuted, maybe, you have already raised that issue of languages.
Right.
So there is a specific question by one Priya RL.
Right.
So the question is, how do we handle the co-occurrence of words in regional languages?
Right. So so break down that question a little bit, and it becomes how do we handle the parsing of regional languages first? That's, I think, problem number one. And well, there has been some work that has gone on there. I know some of our colleagues. I think Kavi Mahesh used to work on this, right, Shalini, and his brother as
Yeah,
well.
Kavi Mahesh has done some work in this. I'm not very familiar with
Right. Yeah.
the depth of the work that has gone on.
Right. Me
He's
either. So,
also worked on ontologies and stuff like that. Yeah.
correct. So there has been a lot of work that has gone on in natural language processing for Indian languages. I'm myself not familiar with the exact techniques that have been used, but uh, in general, parsing uh, regional languages is a lot more difficult than parsing Indian languages, and this is for that difficulty is for various reasons. One is that of course the language itself presents a challenge, right? It's agglutinative, it's it's far richer, and so parsing it becomes more difficult. The second is also that the scale is different, right? The number of users of that language pales in comparison to the number of users of the English language. So it's like the tyranny of the majority, so the English always kind of takes the cake. But also there isn't enough. The question we have to ask is there enough digitized content available, right? Have we digitized enough of the regional language content in order to be able to start you know playing with it to develop solutions for regional languages? I think that also is an issue.
Yeah, I do not know the latest thing available in regional languages, but how about the Wikipedia regional, that is Kannada Wikipedia, the text corpora could be used, right? Because right
Yeah.
now, see, when I start, I mean, I did a little bit of work on Indian language content. In fact, we had about, at that time, I'm talking about 2002 or 3, 300 Kannada language thesis, full text available. In
Right.
fact, yeah, that is how I got to know, in fact, Jayant Haritsa, his student Kumaran, who later worked for Microsoft,
Microsoft.
he wanted Kannada content to develop something there. And they used, as you rightly said, you need the text corpora to do any research in the Indian languages. So
Right.
he used my content for developing that algorithm in 2002, 2003. Beyond
Excellent.
that, right now, my question to you, I mean, I had following that and your response. I think now there is enough corpora in regional languages too, because there is a lot of, when you Google it, you will find so much of Kannada. I mean, at least I'm familiar with Kannada content. Okay.
Right.
So I see on Wikipedia Kannada content is there. And as you know, in most of your, I mean, research work today, everybody is using the Wikipedia content as the test bed.
Right. Yeah, absolutely. I mean, Kannada Wikipedia, I think, is a great corpus. I have not personally looked into that corpus myself, but I have some experience with the English corpus. And if that is anything to go by, we should expect a lot of skew, in terms of topicality in any Wikipedia corpus. Basically, wherever there is this crowdsourced effort, quote unquote, where basically people come in and collaboratively create content, right, and emerge. So any document in Wikipedia is essentially an emergent document, right? Several users have had discussions, fights, and there have been a lot of back and forth, and that content has emerged, right? Now, while that is true at the level of a single document, I think it's also true at the level of the corpus itself, right? The corpus itself is kind of evolutionary, and I think we will see biases in in topicalities as well. You don't see enough representation for a lot of topics, right? You see there is a skew for one or two specific topics. For example, in the English Wikipedia, I don't think you'd be surprised if I said that a lot of the articles have to do with the United States, right? Because
no, in fact, if my memory serves me, the data, in fact, Indians contribute quite a lot to the Wikipedia content, English content too.
Right, but I had generated a co-occurrence graph of the Wikipedia corpus. Of course, this was the 2006 corpus. So we're talking, whatever
Yeah.
I'm telling you is at least outdated by 14 years, but I don't expect it to have changed very drastically over the last 14 years, given that it's an evolutionary thing. But what we saw was that, you know, when you looked at connections where the co-occurrence count was, say, over 10,000, right? And when I isolated that subgraph, it's a very small subgraph, maybe about 50 to 100 words, 50 to 100 entities, right? And they are all interconnected with each other with very strong connections. Everything to do only with the United States, right? So those are somehow they find place. Those topics find place in most discourses, and that's how they get mentioned a lot. That's how they co-occur with each other a lot. And I think it's fairly natural as well. You know, I mean, without going into the specifics of why the US is a topic of discussion for the English Wikipedia, I think it does happen that, you know, there is an affinity for specific topics when it comes to any large corpus. But Vivek Kumar has said in the comments, Karnaja is another great corpus. So one of my colleagues worked on it for a while, called Sumant Kulkarni. So maybe that is another source to look to.
Yeah,
There is one question from Rajeshwari K. Rajeshwari, you can unmute yourself. Your mic is allowed to be opened. Could you please unmute yourself? There's a button over there.
Rajeshwari, unmute and ask your question, please. You have her question, otherwise you can ask, then we can
Okay.
because we are running.
She says my mic is not working. Wanted to know how to distinguish feedback of some event handled. We have collected objective feedback and descriptive feedback. Can we prepare a decision tree or a graph-based approach having both objective and descriptive ones? This is the question.
I'm not sure I understand the question correctly. What kind of feedback? What events are this? What is this data exactly?
Okay, so Rajesh,
Otherwise, what we can do, Mandar, is we can, I mean, ask her to give that question a little for the second session. Anyway, we have the.
Sure.
Yeah, maybe with a bit more description.
So we will break for our break. Okay, we'll break now and then come back. So we have overshot by about 5 minutes. So instead of, let us say 11:45, 11:50, we get back. Okay.
Shalini, before you break, can I ask a question to Mandar?
Sure.
Yeah, Mandar, you know, there were questions about reference service in libraries. They get lots of questions, some simple questions like, you know, reference questions we call, what the height of Himalaya, or how do I find a good manufacturing process for a chemical which gives me a higher yield. So anything from, you know, cricket score simplicity to a genomic complexity. Now, that takes me back to what IBM did, the Watson machine you created, and then that became the most successful machine in the answering the quiz, in beating the champions. And that's exactly typically how a reference service works in a library.
Right.
Imagine if all the corpus of, you know, all the material, all the text in the area of, let us take, for example, chemical sciences, all articles and reference books are digitized. There must be a few million articles, you know, with taking out all the chemical formula and whatever else. Now, can something like Watson machine, which you have already implemented in medical area, can it really answer the question straight away to users when you ask the question? A complex question like, what is the manufacturing process, most effective manufacturing process for this product?
Right. Great question, Mr. Satyanarayana. So I'd like to answer this in two parts. One is that when we talk about you know, technology suites like Watson, right? we need to understand that Watson is the name given to a set of services, technologies, APIs, and so on, right? And products. Now, when we say that, when we look at Watson, that played Jeopardy, that was a specific solution. So it was a specific solution built on an encyclopedic corpus. So that is why it was able to answer questions, that were also encyclopedic in nature, which is mostly general knowledge, right? Now, can you take a Wikipedia corpus and segment that information, index it properly in Elasticsearch or in Watson Explorer or somewhere, and then put a chatbot as an interface, so that when you ask a question, that question then gets translated into an API lookup for whatever is the data store where this information is stored, and it comes back with an information, gives you an answer to your question? Yes, it is possible, but we would have to figure out what is the source of the data, right? So when we talk about Watson or any other technology today in the market, right? What is sold is what's available is the technology, the solution, not the data. The data will still have to come from us. The data has to be with the enterprise. Only then these solutions will make sense, right? So it's never the solution bundled together with the data. So in that sense, uh, we can develop these reference solutions to answer specific questions, but those answers, that repository of knowledge has to be present in the enterprise already, in the library already, right? That's one part. The second part of my answer is that it is possible to have models and solutions that are built on one repository, that have an understanding of one body of knowledge, and then build on top of them, right? So you have a model that has been trained on some data. Now it is possible to transfer this learning, right, into your data. Essentially, you augment the learnings from your data onto this model and build on top of the learning that it already has, and this learning was on some generic data, right? So that's the two levels in which I would like to answer your question. So if there is a model or a solution that's already built on some data, then we can employ techniques like transfer learning in order to augment that learning and make it capable of answering questions specific to your domain. So in that sense, that solution does not come with zero knowledge. It comes with some basic knowledge, but some generic knowledge, and you train it to answer specific questions. That's one part. But the other part is that, and this probably is the most uh, it's probably the most general answer here, which is that you have solutions, you have algorithms, you have models, right? And those are available for deployment. The data is not with the solution provider. The data is with the people who want the solution. It has to be in the enterprise always.
To add on to that, Mandar, right now, and Satya, for example, Google and Wikipedia are collaborating together to enhance their knowledge graph, and that's how their question answering system is working now. Because I mean, the old reference questions that would come to libraries, the Google can answer now most of the time, because Google is already has a formal partnership with Wikipedia and Wikipedia content, etc., and which they are using it for question answering, as well as for even things like what we talked about earlier, the local language or Indian language or regional language translation issues, all that. So slowly we are moving towards that kind of a you ask a question, who is the simple one, I'm saying, like the way you said, which is the highest mountain or something, Google answers that, but it also sometimes just takes you to the source of the article.
Yeah, I mean, certainly the collaboration with encyclopedic bases like Wikipedia helps, but I think the biggest thing that works for Google, in favor of Google here, is that their data is essentially whatever is on the internet, right? Or whatever is crawlable on the internet, right? Much of the internet is not crawlable even today, but that they go and crawl web pages across the internet and put it in their database. So they are themselves building an enterprise there. They have their own data enterprise on which they are basing, this question answering. So several times Google can answer some questions that are fairly complex, and those answers you will not find in Wikipedia. For instance, if you just try this, what's the date today? I'm fairly sure it will answer that question, right? Now that's a reasoning that's beyond looking up something.
Yeah.
Yeah.
You're right. I mean, talking about Wikipedia or Google and AI, and you are in the initial period, you said AI is the goal. In fact, Wikipedia at one time said that, what is their objective is to be the artificial
Exactly. Yeah.
intelligence.
So exactly, and that underscores
that is their company's goal, to be the artificial intelligence.
right. Exactly, and that underscores my point that AI is not. It's actually a goal that you want to achieve. It's not a technique or a set of. It's not a technology by itself.
Okay, I think we have already overshot. So we come back and meet at now 12. Shall we cut short the break or shall we cut short the lecture? I think half an hour break is necessary. So I request all the participants, we don't want to lose you, audience. So come back at 12 sharp. Okay. So we will meet you, resume the tutorial at 12 noon. Thank you, Mandar. Thank you, everybody, for your questions. But for the next session, I would request each one of you to be ready with your question to ask the question yourself, rather than just putting it on the question box. Okay.
So let me just quickly, in a couple of sentences, say what's coming up in the next session.
Okay.
We're going to talk about an introduction to neural networks at a very conceptual, very basic level again. We're going to talk about one other example of classification. We're going to talk about naive Bayes. We're going to talk about one clustering algorithm, and then we'll talk about some open issues in AI, some open challenges in AI.
Okay. So you know what to look forward to in the next session. Okay. So have your lunch or whatever, brunch and whatever you want to eat, something, and then come back at 12 noon. Okay. Okay. Thank you. Bye.
Thank you, folks. See you.
Okay. Hello, friends. Welcome back to the second session of today's workshop on AI for eScience. I suppose all of you are really back. Okay. Before I hand over the platform to Dr. Mandar Mutalikdesai, I would like to make one small correction because Mandar was saying about another workshop in the afternoon. Actually, it is tomorrow afternoon. We have the workshop on semantic search technology, or semantic search, the current frontier of search technology, by Ricardo Beza-Yates, who is currently a professor at Northeastern University at Silicon Valley. Formerly, he was the CTO of Intent, and he was also the VP of technology at Yahoo, etc. So he, and also the author of the very well-known book, Modern Information Retrieval. So it's a classic, actually. Modern Information Retrieval book by Ricardo is a classic. So he'll be giving the workshop on semantic search tomorrow at 3 p.m. So if you have not registered, please do register. Okay. And then I would also like to make a mention about our actual conclave. These are all the pre-conclave events. The conclave is on 27th. So the inauguration keynote is given by none other than Professor Tony Hay, who is considered as the father of eScience. He's currently chief data scientist at the Technology Facilities, Science and Technology Facilities Division of the UK Research and Innovation Council. So please register for the main conclave, which starts from 27th and goes on till 30th. And apart from the inauguration, we have 6 thematic sessions. The first one is on science as the fourth paradigm, the eScience, the fourth paradigm of research. Second one is on open science and scholarly communication. The third session is on cyber infrastructure and big data analytics. The fourth session is on research data management and libraries. The fifth session, that is on the 30th, is on social media and research. And the sixth one is on health informatics. So these are the 6 thematic sessions that have been planned for the LTC 2021. So I invite you all to register for the main event as well, in addition to tomorrow's workshop. So with this introductory remarks, now again I welcome Dr. Mandar Mutalikdesai, and over to you, Mandar.
Thank you, Professor. Okay, so let's resume, and my apologies for that gaffe. So yes, the talk by Ricardo is by is tomorrow, not today. Okay, so just a quick recap. We have talked about representation of documents. We have talked about similarity measures. We talked about spatial measures such as the LP norms, taxi driver's distance, L1 norm, or the L2 norm, which is the Euclidean distance. We talked about cosine distance and saw how effective it was when you have scaled documents, right? So now let's talk about classification. And I would like to specifically talk about one particular algorithm, the naive Bayes classifier. So this is, of course, it's a foundational technique, and is a great way to start understanding classification itself. But it is also underrated in that it performs really well, and you will see why it is called naive. And there is actually there isn't much that is really naive about it, because it works quite well in the real world in most applications. So you're all familiar with the Bayes model for conditional probabilities, right? So if you have, let's say, so the equation is on the left-hand side of your screen there, right? The probability of C given X is the probability of X given C times the probability of C over the probability of X, right? So, or in other words, P of C given X times P of X is the same as P of X given C times P of C. So let us put this in context, right? Let us ask the question: given that, let's say you're at a university, and you're just going around the corridors of the university, listening, taking a look at what's happening at the different classrooms, right? Now let's say you come across a class where you hear that NLP, computer vision, and speech are being discussed, right? Those are the topics that you hear being discussed in that classroom. What is the probability that this is a class on artificial intelligence, right? So if you want to now posit this question in terms of conditional probabilities, you would basically ask, what is the probability of AI, artificial intelligence, given NLP, vision, speech have occurred, right? So what is the probability NLP, vision, speech would be discussed in an AI class? That's the first question, right? So you want to understand what is the probability that the class is AI given that NLP, vision, and speech are being discussed. I now ask you, okay, given that there is an AI class, what is the probability that it will have the topics of NLP, vision, and speech, right? And what is the probability that an AI class is taking place at any given point of time in the first place, right? So when you ask those two questions, those become the numerator, right? The probability of X given C is the first question, and the probability of C is the second question. What's the first question? What is the probability that NLP, vision, and speech would be discussed in an AI class? And what is the probability that an AI class would be taking place in the first place, right? Now the denominator is, what is the probability that NLP, vision, and speech would be discussed in any class in this university, right? So let's take all classes in which NLP, vision, and speech would get discussed. That forms our denominator. And in the numerator you have, okay, now of all these classes, okay, what is the probability that an AI class will have speech, vision, and NLP? and what is the probability that an AI class is taking place. So that should conclusively tell us what is the probability that the class is AI, given that NLP, vision, and speech have been heard of. So that is the basic notion of the naive Bayes classifier, right? So you heard certain features, you heard NLP being mentioned, you heard computer vision concepts being mentioned, you heard speech being mentioned, speech processing being mentioned, and you are interested in classifying this class now, right? This lecture. You wanted to identify what class does it belong to. Is it the class of artificial intelligence? Is it the class of information retrieval? Is it the class of mathematical foundations of computing? Which one is it, right? Now, when you ask that question, what the model did is it said, okay, now when I look at my previous data, right, let me first identify if there is a class for AI, what is the probability that NLP, computer vision, and speech have been discussed in it, which is another way of saying what is the probability that this class will have these features, right? And what is the probability that the class itself is occurring, right? What is the probability of the occurrence of this class in the entire universe of discourse, right? And let's weigh that. Let's weigh that in proportion against the occurrence of these features across all the classes, right? So essentially, now you said, okay, what is the what is the probability that NLP, vision, and speech would be discussed in any class, right? I'm sorry. So the question we asked was, what is the probability that the class is AI, given that NLP, vision, and speech are being discussed, right? That is like saying, what is the probability that AI is being, what is the probability that NLP will be discussed in a class on AI times what is the probability that vision will be discussed in a class on AI? What is the probability that speech will be discussed in a class on AI times the probability that this is in fact a class on AI itself, right? Now, as you can see, NLP, vision, speech, modeling, machine learning, all of these different features, they are all inexorably connected to one another. They are all dependent on one another. They are not independent, right? So you cannot ask the question independently and say, let me determine whether this class is an AI class by just looking at the feature called NLP, by just looking at the feature called computer vision, right? That will not work. But that is in fact the assumption that this algorithm makes. It says that I'm going to assume that all these features are independent of one another, right? And because this independence assumption is inserted, it's known as a naive independence assumption. Of course, it is naive meaning simplistic, because in reality, these features are really not independent of each other. They are highly dependent on each other. They occur together for a reason. They occupy a meaningful subspace together. So they should not be separated from one another. But for computational ease, the naive Bayes classifier modifies the Bayes equation in saying that I will treat all the features separately. So when we talk about P of X given C, it says, okay, if P of X1 given C is separate from P of X2 is given C is separate from P of X3 given C, and so on, right? So with that caveat, you have the naive Bayes classifier. Now, I want to get to the part on neural networks and spend some time on that, a very basic introduction to neural networks. But let's talk about clustering also quickly, right? Now, the basic difference between a classification algorithm and a clustering algorithm is that they are essentially two different paradigms of machine learning, right? In classification, as in this case, right? If you want your model to be able to recognize the class as AI, then you have to show it enough samples of an AI class. meaning that there have to be enough lectures that are annotated as AI and used as training data for this model. So for every class, you will have to present enough samples and let the model learn these prior probabilities, right? Such as P of X given C, P of C itself, P of X, and so on, right? Which means there is supervised learning. You are creating annotated training data and learning a model based on that, right? So that is supervised learning. But many a time you do not have access to training data, which is labeled data, right? And in which case you resort to an unsupervised way of learning the groupings of documents, which is known as clustering. So there is no labeled data which can help you learn the decision boundaries between these various groupings of documents. So K-means, again, it's a very basic technique, but serves very well to understand how clustering works. And also, if you can decide on the K appropriately, then it's a rather effective way of doing clustering. Now, let's go back to our representation of documents, and again start imagining your corpus of documents as points in a multidimensional space. So imagine the room that you're sitting in, and let's imagine a scattering of points in that room, right? Now that's your document corpus. Now the task at hand is to identify what are similar groupings of documents in this space, right? What are clusters of documents? What clusters of documents can we identify? How do we draw those decision boundaries around subsets of these points, so that we can say, okay, this is one cluster of points, this is another cluster of points, and so on, right? Now, in order to do this in K-means, what we need to do is, first we need to decide K, which is what are cluster centroids, right? These are points. Cluster centroids are points that are representative of each cluster. So if you say my K is 5, it means you are already making an assumption that you are going to determine 5 clusters out of this scattering of points in space in this document corpus. Okay. Now, why K is a very pertinent problem, and there are ways of determining the right number of clusters, the right value for K, but we will not go into that at this point. I'd like to refer you to methods such as the elbow method, which kind of help you explore your data and determine what would be the right number of clusters for you to find out, for you to determine in your data set. But for our purposes today, let's assume that K is a given. We already know what is K. We know what is the number of clusters we want to generate. Now the question is only, how do we generate these clusters, right? So let's assign 5 random centroids in our space, okay? And now we're going to start building clusters around this space, around these 5 centroids. What does it mean? It means we have to start taking each point, each document, and assign it to one of the centroids, right? Assigning the document to one of the centroids, the best possible centroid. Now, what is the best possible centroid? Based on similarity. So let's assume we are using a technique like Euclidean distance or cosine distance, right? There is some similarity technique using which you are determining what is the closest centroid for a given document, right? So you assign your random centroids, and then you do the first round of assignments, meaning you will iterate through each document and each point, and you will do a similarity comparison of that document with each of the 5 centroids, and then you will assign that document to one of the centroids, the closest one, right? Now, once you have done this for all the documents, right, you will have the first cut of what will eventually become your clusters, right? Except this is not your final version yet, right? Why? Because whatever centroids you had chosen earlier, right? The word centroid has a specific meaning. It is not just a representative of the cluster. It's a point in that cluster that's basically the harbinger. It's what it's what, well, I did use the right word earlier. It represents that entire cluster, which means that it has to be the most quote unquote central point, right? It's a centroid, right? So if you remember how centroids are computed, if you have, say, 3 points in a two-dimensional space, x1, y1, x2, y2, x3, y3, and you want to compute the centroid for these 3 points, then you say x1 plus x2 plus x3 divided by 3, y1 plus y2 plus y3 divided by 3, right? That becomes the centroid, right? Now, when you have completed your assignments for each of these cluster centroids, you have to recompute the centroid now, because whatever point you had randomly assigned in the first iteration as the centroid, it may not really remain the centroid anymore, because there are far more points that have now been assigned around that particular point, and the centroid now needs to change, right? At which point, now this is a good time to remember that whatever centroid you assign to each cluster, that centroid need not actually be a point in space. It need not be one of your input data points. It can be an arbitrary point in space that you make up, right? So now you recompute the centroids. So let's go over this again. You first assigned 5 random centroids somewhere, and then you compared each document with these 5 centroids. I'm assuming K to be 5. You compare each document with each of these 5 centroids and assign that document to the closest centroid based on similarity. Once you have done this, you now take the cluster pertaining to each of the centroids and you recompute the centroid, right? So now the centroid is a lot more centered, quote unquote, right? It's a lot more in the middle for each group of points. And then you repeat the assignment. So now that the centroids have changed, maybe the assignments will also change. So what was a point that was earlier assigned to centroid 1 may now be assigned to centroid 2, because the new centroid 2 is closer than the previous centroid, than the current centroid 1, right? So you keep doing this iteratively. You assign centroids, you assign documents to the centroids, then you recompute the centroids, and owing to the recomputation of centroids, you now do reassignment of the documents. After doing the reassignments, you again recompute your centroids. So you keep doing this in a cycle, right? Centroid recomputation, reassignment, centroid recomputation, reassignment. You keep doing that in a cycle till it is not possible for you to do any more new assignments. So it will converge at a steady state where no new recomputations are possible, no new centroid recomputations are possible, and no new reassignments are possible. It will have arrived at that steady state, at which point that's theoretically the end of your clustering process. Of course, practically speaking, you need not do this infinitely till there are no more assignments possible. The convergence can be attained much sooner based on practical considerations, when basically the number of assignments reduces to an acceptable number. You can stop, practically speaking. Right, which brings me to neural networks, and we still have about 40 minutes to go. So let me spend a little bit of time on this. I think this is one topic that does evoke some interest, and I'd like to address this topic at a fundamental level. And I discussed this with Professor Shalini as well, and we said, because it's a tutorial, let's address it at a very fundamental level, and try to explain the concept, right? So what are neural networks? So everybody has seen the picture of a neural network. Everybody has seen a pictorial representation of a neural network. You have inputs, right? You have an input layer, so x1, x2, x3, and so on, right? And you have an output layer, right? The output layer could be, say, classes. The input layer could be just like you represented your documents as points in space, right? So let's say that a document is represented using its TF-IDF, and a document vector is represented using its TF-IDF. So now what we could do is we could take each vector, each document, and every component of that vector, essentially becomes the input layer, right? So you take all the components of this vector, then those components together become the input layer. So x1, x2, x3, x4, x5 are basically the TF-IDF values for the first dimension, the second dimension, the third one, the fourth one, and the fifth one, right? That's how your document is represented. So that's the input. So the input is essentially your document, and this is just one example I'm giving. It can be adapted to other use cases. And the output layer is determining what is the class of this document, right? For example, is this document about AI? Is it about fiction? Is it about politics? And so on and so forth, right? And between the input and the output layers, you have a bunch of other hidden layers of neurons, right? Now, what do these neurons do? So from one layer to the next, right, there is an intricate connection, right, between neurons. So there is information being passed from one layer to the next, as you can see in this picture. Here I have shown only one hidden layer, right? Now, each of the neurons in the hidden layer perform a computation, right? They perform a computation based on the input that they receive from the previous layer. In this case, the hidden layer is receiving its input directly from the input layer itself, which is basically the TF-IDF of a particular document. But in general, the input to a hidden layer can come from the output of the previous hidden layer also. Okay, so that is generally how a neural network architecture looks like, right? So there are layers of neurons. There is one input layer, there is one output layer, and there is a bunch of layers in the middle known as the hidden layers, and there is the input for each intermediate layer is coming from the previous layer, right? Now, what we know solidly so far is that there is an input, right? And the input x1, x2, x3, or whatever is basically the TF-IDF vector. X1, x2, x3, x4, x5 is the TF-IDF vector for my document. And we know that the class, the output is the class of the document. So given a particular document vector, this neural network is capable of telling you whether this is a document on AI or on fiction or on politics and so on, right? Now, there's one crucial element here, which is the weights on the edges, right? So if you look at any cell, any neuron in layer 1 and any neuron in layer 2, there is an edge there, right? And that edge will carry a weight. Okay, so if we assume the output of the hidden layer to be some y, and how that output came, we will come to that in a moment. So there is some computation that happens in the hidden layer, and a y is computed, and a value y is computed. Now this value y is computed based on two things, right? The input, which is the xi. Let's say the input is coming from x1, x2, x3, x4, x5, right? And the associated weights. So from x1, there is a weight coming from w11, right? From xi and wij, you are computing yj. Okay, so that is the computation that's happening. Okay, now what is the computation? What exactly is the function? Let us call that function g. So yj is g of xi comma wij. Okay, so let's just keep that in mind for now. Just to recap, there is an input layer, there's an output layer. The input is the raw input. It could be your TF-IDF inputs. The output is, say, your classes, for example, in this use case, in this example. And every intermediate layer receives an input from the previous layer based on a certain weight on the edge from the previous layer, and it computes a new value based on a function. So yj equals g of xi and wij. That's what we are going to keep in mind for now. Now, what I've done here is just look at the first neuron in the first layer and the first neuron in the second layer. Okay, just take that. There's the first neuron in the first layer and the first neuron in the hidden layer, the second layer. Just take those, and that's what you see here. Okay, so that X is coming from the input layer. The Y is being computed in the hidden layer. The X is coming through an edge with a weight W, and the function G is being performed in order to compute that Y in the hidden layer. Okay. Now suppose G is a simple linear function. Suppose G is a simple linear function where Yj is simply the multiplication of W and X. Okay. If Y is just W times X, what does such a neural network represent? It looks like Y equals mx, right? Y equals Wx looks like Y equals mx, which is basically a straight line. It's a linear regression model with x-axis, y-axis intercept as 0. There is no c here. There's no plus c. You only have y equals wx. You don't have plus c, which basically it is plus 0. So this is the linear regression model with 0 as the y-axis intercept. Okay, if we assume G to be a simple linear function. Now let's take one step back. Okay, let's go back to this diagram. What we are trying to do here is we are trying to evolve a notion of computing based on neural networks, actual neural networks from the animal brain, right, in the human brain, for instance. Now let's consider a scenario where the input coming into the human body, to the brain, is you touching a surface. Okay, I don't know if you can see me now that I have my slides up, but I am holding up a bottle here, right? So this is a steel bottle. Now me touching this bottle is the input. Okay, so there are several parts of my palm that will be touching this bottle here. Now let's say the heat felt on the different points on my palm are the x1, x2, x3, x4, and so on. That's the input layer. Okay. Now what is being learned through this neural network is, once I touch the bottle, how should my brain react? Right? Once I touch the bottle, how should my brain react? Right now, this is a cold bottle of water, so my brain doesn't react. Now let's say the water in this is at 80 degrees. Okay, I touch this, my brain still doesn't react very harshly, right? I would go, oh, it's hot, right? But now when I pour water that is, steaming hot into this and I touch it, I suddenly react very differently, right? So I want you to picture this. So let x-axis on your, let's draw one chart, and let x-axis on that chart be the temperature of the water. Okay, and the y-axis, let that be the intensity of the reaction. Okay, now as the temperature of the water increases, does the intensity increase linearly? No, it does not. It's not like at 0 degrees I'll do this, and at 10 degrees I'll do this, 20 like this, 30 like this, 40 like, no, it's not like that. The intensity is different, right? As the temperature increases, suppose you have some liquid at say 130, 140 degrees in this, and I touch it, my reaction is going to be a lot more violent. It's going to be non-linear, right? Just bear that in mind for a moment. But let's go back to this G still being a linear equation. Okay, so essentially what happens in your brain is that you got this input from this layer, the cells on your palm, and that gets transmitted, and then there is a layer, that there are several layers, there are several hidden layers, right, each of which receives input from the previous layer, does its own computation about how much should be the reaction, and passes that as the input to the next layer, till the output layer determines just exactly what the reaction should be. So that's at a very crude and a very, very vague and a very trivial level. I'm trivializing this incredibly, right? So that's generally just to give you an idea of how the brain works. Okay, but let's forget the nonlinearity for now. Let's go back to this function being linear. Now, what I'm going to do is generalize this and say that we are also going to enable. So we saw that if this g were a linear function, then it's essentially just a a linear regression model, right? It can fit a straight line to a set of points. That's what it means, right? And it means that the reaction of your brain, regardless of the temperature of the water, will be linear, right? If the brain really worked like that. Okay, but here the problem is that this straight line that you're fitting, right, the data points that are represented, they all that the straight line meets at the origin. There is no y-axis intercept, right? So let's generalize that a little bit first. Let's say non-zero intercepts are possible, which means that if you have y-axis, then it won't necessarily be a straight line passing through the origin. It could pass through a different point on the y-axis. So in which case we will now add an intercept called b, and we'll say y is w, which is the weight on the edge, times x, which is the input, plus an intercept b, a bias b that is coming from elsewhere, right? That is coming as input. Okay, so this is what it looks like, right? So now it's not necessarily passing through the origin anymore. It can pass through any point on the y-axis, right? But still it is explaining only a linearly represented set of points, right? Let it remain like that. Let's still assume that our neural network, an actual neural network, does react in a linear way, works in a linear way, right? Assuming that, the question I want to ask you is, what does learning mean? We say, okay, let's learn a neural network, right? Let's train a neural network. And then you say, okay, the neural network has learned. It has learned its weights. What does it mean? It means learning the right value of W and B so as to be able to fit this line as accurately as possible, right? So learn the right value of W and B so that Y equals WX plus B. That straight line represents the set of points that you're seeing accurately, right? That's what it means. I'm sorry, I'm having a bit of a runny nose, so you might hear me kind of sniffling a lot. So, right. So now the task is to learn the right Wij and B at every cell in every intermediate layer, in every hidden layer, right? W, also known as weights, and B, also known as bias. The intercept is what we're calling bias here, right? Learn the weights and then check how good is that straight line, right? Learn that W, which is essentially the slope in this case, right? And then check how good is that straight line that fits this data, right? Essentially, what's the goodness of fit to that straight line. So you could you could compute a mean squared error, you could compute an R-square coefficient to determine how good that line is, right? And now your effort would be to minimize that error E, right? How do I minimize that error E? So because you don't know what should be the right W, so you start learning the W, you use a certain value for W and B, right? And then you come up with one straight line, and then you see how well that fits, and then you may learn that the error is very huge, right? Now you will look to minimize that error. So it becomes an optimization problem, right? So you iteratively try to minimize the error, right, by learning better and better values for W and B, right? So essentially you measure, how do you minimize the error? By measuring what is the change in the error, right, as I change the weights, right? That's how you start measuring the error, and you start minimizing it. At the point where your error is minimized, those are the best W and B that you have learned. So essentially, neural networks is about learning the right weights, the optimal set of weights and biases such that your error is minimized. Now, let's go back to a classification kind of example. What does error look like? So we talked about error when you fit the straight line to data points, but let's also interpret it in terms of a classification problem, right? Error is basically, so the class should have been C1, but it was predicted as C2, right? So that is the error. So you can measure the error in terms of a difference in the probability distributions. So it should have been 1 0 0 0 0 for your 5 classes. Instead it is 0.1 0.6 0.2 and so on, right? So then you say, okay, what is the difference in the error here, right? Am I 2 off? If you're 2 off, then you've got to start converging towards a smaller amount of error and learning better weights. So again, just to recap, let's assume that the human brain works in a linear fashion, learning from one layer to the next linearly using an equation like y equals wx plus b, right? Which would mean that, and it produces an output, and then it says, okay, this output is very different from the output that I was expecting, so the error is very high, and now I'm going to optimize that error, minimize that error by learning new weights that fit the curve better. So you keep doing this till you minimize the error, and then you arrive at the right configuration of weights and biases, so that your prediction is now as accurate as possible given the data, right? Now the question we will ask is learning really linear, right? Go back to that example that we took of this bottle containing some water of varying degrees of heat, right? So first time it will contain something that's really cold and I touch it and my reaction is something. Then it contains a 50 degrees Celsius liquid. I touch it. Yeah, it's still kind of tolerable. But the moment at 80 degrees, it's still tolerable, right? At 90 degrees, it's still kind of a little less tolerable, but still okay. At 100 degrees, it's intolerable, right? Suddenly, the reaction, the intensity of the reaction that my brain has to the heat of this water bottle jumps at one point, right? It's not linear, right? So in this case, the way you can imagine it is the x's here, right, in the input layer are the heat supplied to your skin, and the y's are the reaction, the intensity of the reaction that your brain computes, right? So in that case, the function g, which earlier we said was simply y equals wx plus b, it should not be linear, right? It should be a non-linear function, right? Something that kind of mimics as accurately as possible the non-linearity of the reaction of the brain as the temperature of the water changes, right? Now to mimic, and that is the beauty of the animal brain, right? That the learnings in each neuron from the previous neuron are non-linear, right? And to mimic that non-linearity, what we do is we assume G to be one of various non-linear functions. It could either be a sigmoid function or a tan H. It could be a logistic function. It could be ReLU, which is a rectified linear unit, right? And so on and so forth. There are several activation functions that these are known as activation functions. So each neuron is activated based on an input from the previous layer and the weight of the edge through which that input is being received, plus the bias, right? So that activation is represented by a mathematical function called G, right? Now, there are several activation functions that are available. Just 4 of them I have mentioned here. I'd encourage you to go and take a look at it in further detail. They're known as activation functions. I don't have that specific phrase on my slides anywhere, so you may want to make a note of it. So that nonlinearity of the human brain is mimicked using one of these functions. So you assume G to be a nonlinear function of wx plus b and not just a linear equation. Okay, what I want to do is I want to go back to all of you folks and just do a 5-minute Q&A just to make sure that we have understood what neural networks are. And if you have any questions, if you would like me to explain again. So I just want that feedback, and if you have any questions or comments.
Hello, participants. Any of you have some questions? You want some clarifications? Other clarifications on what Dr. Mandar Mutalikdesai has just now elaborated on? Neural networks or even anything? You have questions?
You can raise the hand also. We can unmute yours from here.
Raise your hand and unmute.
Also check whether there is any question in the question box.
Yeah.
I checked, I did not see any.
It is, I guess.
That was a generic question by Anil
Yes.
Gupta, but not about this, but I think we can take it little later on, but not about the topic that he discussed right now.
Yeah. So I just thought that, because we have introduced, I realized that the audience is coming from various backgrounds, some from an AI background, some not from an AI background, some even from non-computing backgrounds, some from information science, some from computer science, and so on and so forth. So I thought when we introduce this topic, we'll just quickly do a temperature check.
Yeah, I have a question, Mandar.
Sure, Satya sir, go ahead, please.
Now, now you are explaining, with an example of, temperature sensitivity. Now, in the context of information retrieval, and you are talking about classification and clustering. Now, the classification and clustering becomes useful for handling the query during the search process. So I put a query, and the query is in some way matched by the system with whatever classification and clustering technique we have employed, either manually or using the machine. So you retrieve some information. Now, the human, brain is non-linear in its thinking and reaction. Now, in this scenario, when you explained, for example, someone touching at the 90 degree and 100 degree, your reaction could be different from my reaction and somebody else's reaction. Like your reaction to eating chili and my reaction to eating chilies will be very different. So now, in a similar way, when I give a query, my thinking and my context could be different. Somebody else gives the query, his thinking and the context could be different. While you use samples for during machine learning process for creating a classification system for the machine to handle, how do you create the context for the machine?
Lovely question. So how do you create the context for the machine? Basically, how do you interpret the specific neural network that is at play there, the specific model that is at play there? How do you interpret that, right? One way to look at this is that even when you look at animal brains, like you rightly pointed out, everybody has different reactions to temperature, everybody has different sensitivities or spice levels and so on and so forth. And everybody basically has a different way of thinking, right? So let's model each animal's brain, right, as a neural network, right? If we were to do that, I think what we would see is the kind of connections that we see, the synapses that we see between neurons from one layer to the next, the kind of weights that we would see on each of the edges, the kind of functions, that activation functions that we would see on each of the neurons, all of these would be very, very specific to that particular animal. It is something that that animal has developed on its own over years of evolution, right? Let's refer to each such configuration as a neural network architecture, right? A given configuration, for a given set of layers, with each layer having a certain number of neurons, and each neuron having a certain number of synapses to the next one, having specific weights, having specific biases, ultimately resulting in specific outputs, right? That becomes one neural network architecture. So I think the context is in how you learn, how you design that architecture, right? And it's not really designed in entirely here, because the design can be only in terms of the layers and connections between the layers. The rest would have to be learned. That is evolutionary. So the weights that we learn on these edges, the biases that we learn, right? Those really bring in the context, and that context comes from your data, right? So how do I provide context to the model that is at play in my IR system? That context comes to it from the data on which that neural network is trained.
Yeah, got it.
There's a indication from Vaishali Mulik. She has raised her hand. You can unmute yourself, Vaishali, and you can ask the question.
And
Vaishali, can you unmute yourself, please?
in the meanwhile, there is one question in the question box from Pandiraj A. Sir, what is ReLU? R-E-L-U? Is he
Yeah, so ReLU is rectified linear unit, right? It's a specific function. It's a non-linear function. So okay, let's do one thing. You can just Google it. I would have done the same. I don't have it on my slides. Unfortunately, I will not be able to explain it very well without it. But it's a non-linear activation function. It stands for rectified linear unit. Right. So for example, okay, let me do the best that I can. So if you can follow my hand here, right? So a linear function goes like this, right? And with our example, we saw that the brain's reaction is not like this, right? From the brain's output is never linear, right? It is non-linear. It could be linear in some cases, but it's not generalized to be linear, right? So in which case we say, okay, that function G needs to be non-linear. So now, if you say adopt a sigmoid function as your activation function for each for neurons in one layer, right? Then that sigmoid function will give you a curve like this. Like an S, almost like an S, right? Okay. So that's a nonlinear function because it's an S, it's not a straight line, right? Now ReLU is another function that gives you a nonlinear line. It's a nonlinear function. Actually, I didn't expect to go into a detailed discussion on activation functions, so I didn't have any slides, make any slides for it. But
there's one journalistic question, but can be taken in the end. How to implement disruptive technology to improve library services? It can be taken in the end. No problem.
Okay. All right. So
maybe you can resume your lecture, and then we can go for questions if there are any later. Okay.
Sure. Right. So, so far in building this solution, right, for the KYC solution, if you remember, right, for this large bank that is onboarding high net worth individuals by looking at information about them on the web, right? So far in this journey, what we have done is we have talked about how do we represent the documents that we read, right? Whatever documents we crawl as vectors or as bags, as document embeddings and whatnot. And then we said, okay, how do we identify what's happening in this document? How do we understand the topicality of this document? So there we talked a little bit about, very, very briefly about semantic role labeling and named entities and noun phrases and latent semantic indexing, topic modeling, and so on, right? We talked about co-occurrence graphs there. And then we said, okay, how do we organize this information? And as part of that, we talked about a clustering technique. We talked about a classification technique. We talked about a general introduction, very, very generic, very, very basic introduction to neural networks. And now the next stage is, okay, how do I correlate information? And why is that an important problem? For example, suppose I have, suppose the customer who has approached my bank is Shalini Ars, right? But the document that I am seeing, I have a news article in which I see the name S. Ars being mentioned. Shalini's name is not mentioned in full, right? So now there is a question of entity resolution. To be able to say that John Doe is the same as J. Doe, which is again the same as John D, which is again the same as John P. Doe, or which is again the same as JP Doe. All of those variations of names belong to the same person, to the same entity. That's known as entity resolution, right? And here again, I'm presenting these to you as problems. I'm not going to talk about ways to solve these problems. There isn't one way to solve these problems. There are actually entire products built around entity resolution. Then you have the opposite problem, which is entity disambiguation, right? If you see J Doe, if I say, for example, if I say S Ars being mentioned in an article, how do you know it's not Srijay? How do you know it's not Srijay Devrajas? How do you know it is Shalini Ars instead, right? Because they're two different entities. So now you have to disambiguate and say J Doe could either be John Doe or it could be Jane Doe, right? And there is that disambiguation. There is that ambiguity inherent in J Doe. How do you disambiguate this now? And then you have the regular problems of word sense disambiguation and polysemy, right? For example, the word jaguar, right? Now, jaguar has a different meaning in different contexts, right? For example, in the context of animals, it's a specific kind of, it belongs to the family of cats. It's an animal, right? A carnivore. But it in the context of automobiles, it's a car, right? So how do you disambiguate the sense of a particular word, of a particular term, right? How do you look at words that and jaguar is at least a noun, an entity. There could be certain words which float across entities as well as other parts of speech. For example, bank. Bank could be a noun, which means a financial institution. It could mean another noun, which means a riverside, the bank of a river, or it could mean the banking of a road, right? It could mean bank as in a verb, which means to rely. It could mean so many different things, right? How do you disambiguate the sense of these polysemic words? So that is where that's the kind of problem you need information that you have collected from various sources. So that kind of more or less brings me to the end of some challenges when it comes to natural language understanding, natural language in general, right? We talked earlier about how we have mainly been discussing English, right? We talk about any activity, any natural language processing task. We have more or less placed it in the context of English, right? But what about most of the other world's languages that are agglutinative, local languages, right? where morphemes just get strung together, they just get fused together, right? What about tonal languages, right? Now, this is a very interesting concept. Do you know that 70% of the world's languages are such that given a particular word, how you utter that word changes the meaning of the word? That's 70% of the world's languages, right? So if you have languages like this, then we have to, you can even go beyond NLP and ask a general question about AI and say, how do we address problems like speech to text transcription, right? If you say I have a speech to, somebody says they have a very efficient speech to text transcription service, you've got to ask, okay, does it handle tonality, right? Because if I have a word and I utter it with a different tone and a different pitch, it means a different thing, right? Can your API, can your service really detect that pitch and that tone using which I have uttered that particular sound and thereby infer the meaning, right? So that's a question that we've got to ask. And it's a big challenge, right? To develop acoustic models, to develop language models, to be able to make sense of that at that level, to be able to make sense of agglutinative languages and tonal languages. And imagine if a language is both agglutinative and tonal, which I suspect is a huge number of languages in the world, right? So how do we process such languages? How do we get algorithms to understand them, right? Let's come back to a basic question. How is sentiment embedded in text, right? So if you see an email, this happens a lot, right? So if you see an email from your boss, you try to infer whether your boss is writing this sarcastically, are they writing this, are they angry with you, are they upset with you? You try to look for tone in that text, and it's probably there. It's there because it was put by another human there, right? The text was written by another human, so there is sentiment, there is tone in that text, but that text has completely dumbed down the tone and the sentiment, right? How do you now embed that sentiment in the text? How do you infer sentiment from text, right? How do you infer tone from text, right? A social tone, a behavioral tone, or a linguistic tone, right? How do we infer all this from text? So there are various such challenges that natural language processing is currently addressing. It's a very exciting area to be in. And as for AI in general, right, one of the biggest problems that I just want to quickly touch upon is bias, right? For example, you may have heard about this bot that Microsoft released. It was called Tay, Tay, Tay. I don't know, maybe some 2-3 years ago. I can't place it exactly on the timeline, but it was a Twitter bot that would learn on the go, right, and learn to have conversations with people on Twitter, right? And one of the first things that Microsoft Tay said was, it's great to be here, and what a wonderful world, and people are beautiful, something to that effect. Said very nice things about people, right? 24 years later, it was saying, 24 hours later, sorry, 24 hours later, this thing is saying anti-Semitic things, right? It is making racist comments to people just 24 hours later, right? Why does that happen? It's because this model is learning bias, right? It is learning from biased data, and it is learning from biased people, right? We have to take accountability for bias in AI, right? Which is why AI ethics is a very active field of research today, right? We take it very seriously. It is as important as making computational advances in AI, in neural networks, in deep learning, right? It's just as important to develop, ethical models, right? So how do we incorporate ethics into computing, right? Asking questions like, should all automatable tasks be necessarily automated? Should it be done at all is a question that we must ask, right? We must ask whether a particular model will have a bearing on discrimination. Does it discriminate against anybody? Does it infuse inequality into the into the context, into the system, into the application? Does it bring in inequity? Does it encourage racism? Does it encourage sexism? And all of these ultimately increase the amount of toxicity in the system. It makes the system toxic for somebody or the other, right? What do we do in order to prevent AI from becoming biased like that, right? And then there are practical problems like data imbalance. For example, you try to solve a classification problem for a client. They'll say, okay, I have, and this I'll anonymize this client, but I have had a client who once came to me with 10 million data points and said, we want you to help us classify these 10 million data points into 500 different classes. I said, that's great, 500 classes, and you have 10 million data points, and that's training data. This is labeled data. There's a lot of things I could do with this. So I started playing around with the data, I explored it a little, and I realized that 9 million data points belong to one class in the data that they have given me. And the remaining 499 classes are represented in just 1 million data points, right? So just look at the skew, right? If you just plot plot a histogram, right, of the distribution of this training data across all classes, right? One of them is 9 million data points. The rest are all barely anything, right? In which case, how do you solve that problem? Because the data imbalance problem is very, very common, right? It hardly ever happens that you will do an AI task where your data is very nicely balanced, very readily usable. Hardly ever happens. You will have to undersample classes that are overrepresented, oversample classes that are underrepresented. How do you do all of that? So there are many more challenges like this, but always bear in mind that we, as AI researchers, as AI developers, as people who look to adopt AI, even if we are not researchers in AI or developers of AI, as adopters of AI, people who aspire to adopt AI to solve problems in the library sciences or in information sciences, we have a collective responsibility to make sure that this AI is not going to become unethical. It is not going to exhibit bias. It's not going to make that system toxic for anybody. With that, I'll just leave you with this slide. And last but not least, I think the biggest question that we are yet to answer, and I think AI is far from answering, is what is meaning, right? I think the answer to that question would really, help us solve a lot of big problems. And of course, there are several bodies of works like analytic philosophy, Vedanta, ordinary language philosophy, neuroscience itself, that have been exploring that question in various ways. But my favorite answer to that question is one by Ludwig Wittgenstein, a student of Bertrand Russell, and a very vocal proponent of the ordinary language philosophy. He said, meaning is use, right? The meaning that you ascribe to an entity is in how you use that entity. I think with that, I'll stop. Thank you for being so patient with me. And I look forward to any questions you have.
Maybe I'll start the first question because I don't see any questions as of now. So that will encourage others to ask questions. I have one question, Mandar. Well, you talked about in terms of, or even Satya asked a question about individual differences, etc., in meaning, in text retrieval and such. But when it comes to AI for, let us say, something like healthcare, in that, when you use it, how do you account for there the individual difference is much more nuanced and much more deeper, right? So how does AI take care of this, I would say, you can call it as bias, because, when you have the data set of, let us say in the US, they do it for white people, and they don't see the problem for non-white people or colored people, etc., right? So how do you take care of that, or how do you address that problem of, I mean, because medicine or healthcare needs to be personalized. It has
Yeah.
to be personalized. And if you use AI, then how will it affect, or how do you address this issue? That's my question.
Absolutely. And medicine not only needs to be personalized, it's also safety critical, right? It could directly lead to the to loss of life, or
Yeah, yeah.
permanent damage to somebody. So how do you take care of issues like bias? How do you take care of issues like race, like you mentioned, in AI like that? Well, this is a really hard problem, and I don't pretend to have an answer to that question. But here's what I will say: that bias that comes into the system comes from the data and from the people, right? Your AI is as good as the data and the people who are building it, right? So that's one thing. So if there is bias being introduced into the data, then the model has no choice but to learn the bias. It's not like the AI has enough sentience to decide to be biased. It just appears to have sentience because it is exhibiting bias, but that bias came from data. It's not something that was inbred within the AI. That said, I think in such critical applications, the way AI is used is as a decision support system. It is not used as a decision maker itself. For instance, if you have AI for let's say detecting various forms of cancer from fMRI scans, right? I think the way the AI system would work is that it would say, okay, I think it would suggest to the surgeon or the oncologist that with a very high probability it could be one of these granulomas, right? Because that's the pattern I'm seeing. But it ultimately acts, I think, as a decision support system to the surgeon or the oncologist themselves, right? It doesn't seek to replace them. So it's up to the domain experts also to decide how they want to use this system. There's one other slightly tricky aspect to applications like healthcare, where you're trying to identify specific diseases, especially in the case of rare diseases, where the genetic makeup of an individual may actually have a bearing on the kind of disease, right? It may be possible that a certain kind of genetic makeup may not get a particular disease, but another kind of genetic makeup may make that community susceptible to this disease. It's very much possible. In which case, uh, again, if we try to be too politically correct and say, oh no, we will not look at race and we will not look at genetic makeup and everything, you're actually losing the point, right? So in some cases, it's not really biased. That's actual good, clean data, right? But it's only when it starts introducing inequity is when we've got to start labeling it bias. Just wanted to put that point across.
Yeah, there is one question from Mr. Saktivel Sami. Sir, could you please unmute yourself?
Yeah, thank you. And just I want to know, I mean, whether you have any kind of block, like there are many groups, for our programming, we have separate kind of block, and Python, we have separate kind of blocks. Similarly, any research block is there for AI particularly, where people can post their research questions or any kind of questions to get to know people can answer it. See, like open source, how we work it, we put our questions open, block, so people respond to that. Is there any kind of groups or particularly for available for you?
Yes, there are several forums where there are discussion threads on topics of AI. There are websites that are now there are platforms like deeplearning.ai by Andrew Ng, which encourage discussion on topics of AI. So you can take a look at those. There are courses, of course, on Coursera, MIT OpenCourseWare, and so on. Also, but if you're interested in blogs, then I'd recommend starting with Andrew Ng's. I think there's a lot of interesting and groundbreaking stuff on that website. Also, take a look at the blogs of Jan LeCun, who works for Facebook, artificial intelligence research, and Joshua Bengio, I think, and Jeffrey Hinton. There are many people who have done a lot of seminal work in this area, and they all have research papers, blogs, discussion fora that they host.
Yeah, thank you. Yeah.
When Lakshmi Sankaran is there, I think she wanted to ask the question. Your audio is already there. You can start.
There is a question from Sangeeta Narang. Anyway, let Lakshmi Shankaran finish, then I'll ask.
Sure, ma'am. I am Lakshmi. Are you able to hear me?
Sure. Yeah. Please
Yes.
go ahead.
Yeah. Okay. Thank you. So we talked about a lot with respect to context building and biases in the classification, for which I think we need to have scores to be assigned for classifying properly. That means it's about weighing the parameters, right? It shouldn't be skewed and things like that. So I think scoring as an algorithm or a methodology is part of statistics. I have a feeling that is not at all touched. We still talk about classification, clustering, and yeah, of course, decision tree, which are very, very rudimentary, fundamental data mining algorithms, which are there for several years. And now I think we should start concentrating more on scoring and statistics. I don't see much is being talked against in many of the forums. So what is your view on this, sir, and where is this happening?
Yeah, that's a very common perception as well. But I'm happy to note that it is actually a misconception. What happens is in popular discourse there seems to be this divide that, okay, we are advanced analytics and statistics people, and we are AI people. There is no differentiation. If you just looked at how we developed the notion of neural networks, right? If that function G, the activation function, is linear, then your neural network is basically a linear regression model, right? So AI suddenly now became statistics and advanced analytics. These two fields are interconnected. It just so happens that they deal with different kinds of data, right? What we call as AI popularly deals with textual data, speech data, image data, right? Basically non-numerical data, unstructured data. Whereas the traditional analytics, advanced analytics, and statistics sciences have been dealing with structured numerical data, right? That is the difference, the kind of data that they deal with. There is in fact even an overlap of the techniques that they all use, right? That just the treatment of data varies, their applications vary, but otherwise they are all part of the same fraternity. They're all part of the same. All of that is artificial intelligence, right? They're all trying to achieve that same objective.
Okay, sir.
Sangeeta Narang, you can ask your question if you are there. Sangeeta? Otherwise, maybe I'll repeat her question because she has put in here. She wants to know, Sangeeta Narang is online. Okay, go ahead, Sangeeta.
Hello, Dr. Madha. It was very nice hearing you. Your lecture was fantastic. Especially, I like that flask thing, the way you explained it and made it so clear. Like it's hot here, or even I was thinking of that divisions also. Like at 0 degree, it's cold, you're holding it there. And if it's at the layer, it's 100, and then you almost retrench. And then how that mapping is done. I was quite curious and wanted to know how your mental, those things, neural networks, and how you correlated with the computer algorithms and all that. It was fantastic. You have simplified the things. I was quite like worried. Something like that was always in my mind. Thanks for clarifying that.
Well, I've just had the privilege of listening to people better than me from whom I have learned this. There are a lot of people whom I'm not crediting for being able to deliver lectures like this. At the beginning of this talk, I told you that Professor Shalini has been one of my mentors. I have had the good fortune of being mentored being taught by people like her, and which is where I've learned all these things.
Okay. I logged in late, but I really felt why I didn't log it earlier. I was busy with certain things and couldn't realize it. But it was fantastic. It was mind blowing for me. I really felt very good listening to you. Okay, now my question is something about sentiment analysis. Like on Facebook, we say like, wow, or take care or something. one thing. And then on Twitter, like we have got how many followers are there, how many followed, the comments and all that things. So how that sentiment analysis is done? Like you have got some closed groups and certain people are really commenting very good about it, or you seriously feel like learning or taking out meaning out of it. So what is that tool, or what is it that can be of use to us, um, for
Right.
finding the information or something like that?
Right. I think needless to say, there isn't one size fits all solution for the question that you're asking. But I'd just like to talk about the nuances that exist in a problem like sentiment analysis. Right. One is where if you look at a pre-Facebook era, right, or even a pre-Facebook era, or even a pre love, take care,
Yeah.
sad
Yes.
era, right?
Yes.
I think there have been two of these eras, right? One is the current era where on social media like Facebook and LinkedIn, now you can explicitly embed your sentiment. And you can say, okay, you wrote something, I either love this or I'm angry about this or something, right? You can make your sentiment explicit. In which case, mining the sentiment from that post is a slightly less complicated problem, right? But pre this era, or even in this era, if you want to look at the sentiment that exists in the text itself, right, that is a major challenge and a major problem to solve, right? Now there are several ways in which this is done. The simplest way is to simply identify polarity words, right? Have a list of words that signify a positive emotion and list of words that signify a negative emotion, and then depending on the how many times each of these words occurs in these texts, you can assign a weighted score. That's probably the simplest way to do it. It's the most basic form of sentiment analysis. But I think sentiment analysis needs to be more nuanced than that, right? So if you were to develop a supervised learning model to do sentiment detection, I think its nuance would depend on at what level of granularity you want the sentiments to be. For example, if it's just good and bad, positive and negative, that's a binary classifier, right? Just two modes,
Right.
right? It's slightly simpler to build that because it's easier to build the training data also for it. But suppose you want to now break it down one level further and say, okay, positive meaning, so there's several positive emotions, right? So happy, satisfying, joyful, whatever. So you break it down one level more, and getting the training data for it becomes harder, right? Maintaining that equitable distribution of your training data and everything becomes harder, right? So in general, yes, building a supervised learning model, deciding on the right kind of model, the right kind of, if you decide to go with neural networks, the right kind of neural network architecture, all of these play a role in how your sentiment analysis engine will shape up.
Yeah, there's a question from
May I ask one more thing? Like, what is the final outcome? Like, the particular comment is really effective or something. What is the final take on it? Like, this particular comment, this particular post or something has really made some change or something. Is that the final outcome of these sentiment analysis?
I think you mean this in the context of social media platforms.
Yes.
Well, it's very hard for us to know what the final outcome is. I think only Mark Zuckerberg can answer that question.
Okay. No, I think it must be like that. The person is really post certain very positive things or something regressive or something.
Well, look, in general, social media platforms have transformed from being platforms for enabling information sharing to platforms for driving narratives. Right? They have, wittingly or unwittingly, they are being used like that. We have seen that prominently in the last 5 years globally, right?
That's right.
So exactly what is the intention behind the dislikes, and there's really no one answer to this. I certainly wouldn't want to venture one.
Thank you so much. I really like that.
There is a comment by Sadachivan. Is he there? Would you like to comment yourself? Mr. Sadachivan, you wouldn't? Okay, otherwise maybe someone else has a next question.
Madam, can I go for it?
Yeah, sure.
Yeah, sir, I'm Rajeshwari here. A wonderful talk from your end. I really, you surprised me by giving all the analogies. So previous speaker has given a lens of comments about your work. It's really good about it. Sir, I had put this on the chat window also. My question is, recently I conducted a codathon at my college. So we had groups of people, students who worked for three different titles. So we had one title like education during COVID, the other one like the sports and travel during COVID time. So entire 60 students were supposed to work upon the same topic, but in separate teams, like 4 in a team or 3 in a team. So we took their solutions also, and we gave their evaluation marks and other things. But we collected feedback from them, like asking them how they felt about the topic and how they felt about their work in online mode and offline mode, how it would have been. So we have like a subjective questionnaire and objective questionnaire. So I'm asking you, like, now,
Okay.
though they are in the same team, they are unaware that what their project title was. Like, one person would have given some other title, the second person, while typing the feedback, he has given his own title, subtopic title he has given. So they are so much varying in their own team, so much diversity is there in their own team. So this was actually perplexed because they are in the same team and they're giving different.
But how wildly do these titles vary?
Yeah, because they are, one is education. We gave them how education should be during COVID. Only this much was the statement. Some people have worked upon timetabling the hybrid education, like half of the class comes to the college, half of them work from home, sitting and listening from home. So they have given us varied solutions. So these varied solutions, though they are in the same team, each teammate, when they are typing their title, they have missed out and they have typed their titles differently. This actually amazed us, one part. The other part is when I have this descriptive and subjective questionnaire, objective questionnaire, how do I analyze them and how do I uh, find out solutions like in the graph based approach, or like when I saw your vector based learning, or even graph based, and that Shiggles, and you told us some things about it. So how can I represent it?
I think the most intuitive way would be to start with a word cloud. So what you do is just count the frequency of occurrence of each non-trivial term.
Okay.
Right, and then visualize. So what you do is you then generate a graphic. Right, there are many word cloud visualization tools where depending on the number of times a word has occurred, its size will be, the font size will be bigger.
Yes.
Right, so you can visualize it like that. That will kind of give you one look at that should kind of give you an intuitive idea about what is the general theme running through your feedbacks.
Yes.
Right, the second would be to obviously do sentiment analysis on each of these feedbacks to see how many of these are positive, how many of these are negative.
Okay.
Right. Okay. And the other is maybe just visualize these as a graph, right? So build co-occurrence graphs for each from each of these feedbacks, right? So take all words occurring within one feedback as co-occurring with each other, right? And start building this co-occurrence graph. So that way you can see how concepts are connected to one another in those feedbacks.
So notes will be the words from their subjective questionnaire.
Right. Non-trivial words. You may want to leave out the stop words.
Okay.
Things like that, but include action verbs, verbs, for example, right? So where they may have suggested something.
Okay, sir. Okay. So thank you so much.
Mr. Sadasivan, you can ask a question. I think you are unmuted now.
Mr. Sadashivan, you can raise your comment here.
Okay, let me read it out what he has mentioned. We had specific solution for IR with indexing and search query. Formulations, query formulations easily usable by LIS professionals. Now it seems with the enormity and complexity of info and data, how LIS professionals can manage the routine process is deeper knowledge of AI, pattern recognition, etc. are required, or will the specialties slip from individual institutional libraries?
Well, I think it's this question, if I understand it correctly, also ties into, you know, how can library and information sciences be modernized? And I think they are being modernized with the adoption of AI, with the adoption of information retrieval techniques. So yeah, I think that's already happening, right? To deal with the scale of data, to deal with the demands of applications, AI is already being used in library sciences. I think maybe Shalini or Satya may be better qualified to answer this question, but I think that that definitely is my opinion.
Yeah, they are being modernized. If your question is primarily for information retrieval and AI in information retrieval, well, that is happening with the information retrieval systems, which the libraries are using. I wouldn't say they're being, I mean, they're being deployed in the library system, because in most of the library systems, whether you are developing something in-house or whether you are using something that is already developed outside through some vendor or some other system, they're already using some of these techniques. Like, for example, let us say text mining techniques, which lead to these things, right?
Right.
That is at the heart of, I would say, when it comes to document analysis and artificial intelligence, text mining is at the core of it. So such things are being already used in the context of libraries. That would be my answer. Satya, you have anything to add?
You see the Mandar, you know, you have Watson on cancer. You have a product from IBM. In that, Watson uses in the backend Medline database also.
Right.
How Medline database is used by oncologists as part of the Watson AI system there, clinical system. Can you explain to the audience? That will give them an idea of different situations, specific situations where AI is practically used.
Yeah, I think two reasons why I can't do that. One is I have not worked with it myself, so I'm not familiar with the architecture of the product itself. I have a very generic idea. Second is I'm not sure I'm allowed to talk about it for IP reasons.
Okay.
I'd just like to verify that before I comment on that.
Okay.
One more question was there from Sadashivan KP. Any generic or domain-specific AI application packages or guidelines to emulate by libraries? Do you think in-depth AI expertise is needed to apply the new possibilities in the real-life library environment? Any packages do you can suggest?
Well, I think packages we have talked about already. I mean, I can't think of one package per se. I'm not an SME for library and information sciences, but there are various ways to implement a solution, like Satya and Shalini were talking about earlier. You could implement a chatbot. You could implement speech to text transcription. You could develop devices for digital libraries that can read books to you, that can basically like verbalize books for you, and you could just listen to them. So there are various such applications possible. As for is AI expertise required for all of this, I want to say no. I mean, you don't have to be an AI expert because you are a library and information sciences SME. I think that's your core value, in bringing in any modern solutions like AI, right? As long as you understand what AI can do for you, and what kind of solutions you can envisage with the help of AI, I think that's good enough. I mean, you don't need to have in-depth expertise in AI per se. I'd rather say it's more important to have in-depth expertise in your own field. If you're an SME, that is probably higher value, and you probably get someone else to be the AI expert for you and say, hey, this is the kind of solutions I'm looking to build for me. I don't know if that made sense.
Okay. Yeah.
I think you already answered in one sense.
Yeah.
For example, I mean, AI is essentially, training data set is important. Let's say whether it's in classification or any metadata. So the training set labeling has to be done by the professionals, that is LIS professionals, and then could be given to the AI people to develop or improve the algorithm better, I would say. See, because metadata is one of the main core areas of LIS professionals, whether they are assigning it to a document or any other, any other object. So I would say because of their expertise, let us take just the, author, title, etc. kind of a metadata. Forget about the data metadata, okay? So that kind of a expertise based on their knowledge as well as the codes that they are familiar with and the standards that are available, if that can be applied to the training data set, I think that is the value add that the LIS profession can do in order to improvise the specialized, AI applications for, let us say, metadata enhancement or automatic metadata tagging, etc. for the objects. That would be my sort of additional comment here.
Right.
Satya, you are asking or you just came online? Unmute.
Yes, you are unmute now.
Yeah, I'm not saying anything, just I came on.
Okay, you just wanted to be visible. So I think if there are no more questions, and we have already crossed the time, and I'm sure Mandar is tired and everyone is looking forward to their lunch also. So I would like to just say thank you so much, Mandar. So going by the comments of many of the audiences, etc., you have done an excellent job of trying to make AI simpler, taking us from the old information retrieval era of modeling, vector model, etc., to the current AI thing. So you've done an excellent job. I'm sure our audience has enjoyed, and they will find, I would say, trigger an enthusiasm in your talk would have triggered an enthusiasm in learning more about AI, particularly they're from library information science domain, to know more and then apply the same to the particular domain, that is LIS domain I'm talking about. Once again, thank you so much. And I would like to thank all our committee members who are present here, at least to begin with, Dr. Anand Bhairappa, Dr. Meera, and then I think Dr. Gowder left. So all the committee members and also the organizers, of course, Informatics India, Satya, and then NIAS. I don't see NIAS member is here today. But anyway, we would like to thank NIAS, Rajiv Gandhi University of Health Sciences, and then the CSR Fourth Paradigm for making all this possible for us, and the core committee members for putting this program together. So thank you everyone, and my special thanks to all the participants who not only stayed with us throughout almost the 3 hours. So thank you for your enthusiasm and interest in our workshop. And I once again remind you that tomorrow there is another workshop that is on semantic search. In fact, in one sense, I would say it's a continuation of today's talk. Mandar mentioned about bias. For example, Ricardo is specializing in bias in information retrieval. So I'm sure he's going to touch upon bias in information retrieval, because recently he has been writing and talking primarily about bias in data. So tomorrow, please register. Tomorrow we have a workshop on semantic search by Professor Ricardo Beza-Edz, who is currently with the Northeastern University at Silicon Valley. And register if you have not yet registered. That is one. And the second announcement that I have is for the register, go ahead and register for the entire program. That is the LTC2021 Conclave program that starts on 27th of January and ends on 30th. I'm just repeating again. So 27th is the inaugural, and we are really fortunate to have none other than Professor Tony Hay, who is a legend in the field of eSciences, to deliver the keynote address, inaugural keynote. And we also have great names for all the 6 sessions and a great panel discussion as well. So go ahead and register, and also check out the details of each program, each session on the website LTC2021.org. Thank you, everyone, and see you tomorrow.
Thank you.
Okay.
Tomorrow, what time it is? You have to
3 p.m. Tomorrow, 3 p.m. So the tomorrow again, it will be 3 to 6 p.m. 2 sessions, and each session would be a 1.25 time, and that is 1 hour for 15 minutes with a break of half an hour, and we reconvene and then resume. So it is like 3 to 4:15, and 4:15 to 4:30 is the break, and 4:30. 3 to 4:15 is the first session, and 4:15 to 4:45 is the break. 4:45 to 6 o'clock is the second session.
Okay, thank you, Mandar, and it was an excellent training session presentation.
Thank you.
Thank you all again.
My pleasure.
See you all tomorrow.
See you. Bye.
I'll catch up with you soon again.
Same here. See you.
Thank you. I'll end the session now. Thank you.